Hello, hello. So, welcome to day 3 of scientific computing. We have this 10 minutes together to break the ice. Today we have a couple of new instructors. So,
Good
with
morning.
us today, morning, Susa. Susa, you know her already. But we have also some new faces, Lauri and Johan. So, Lauri, do you want to briefly say something about yourself?
Yes, hi everyone. I'm Lauri Niemi. I work at CSC Finland, which is the Center for Scientific Computing. We host supercomputers for Finland and also some Europe projects. I have a background in physics, so hello there. And yeah, nice to meet everyone.
And with us, there's also Johan, directly from Sweden. Hello, Johan.
Yeah, hello. Good morning, everyone. So my name is Johan Hellsvik. I work at the PDC Center for High Performance Computing at KTH in Stockholm. And there we operate the supercomputer Dardel, which is it's a smaller sibling computer to Lumi, which you have in Finland. And I also have a background in physics, and yeah, with that comes that I'm often using some old compiled languages. Fortran in my field is common. Now more and more, and we will come to that in this lesson also, I'm also combining it with Python.
Excellent. And today, so you can already feel HPC, high performance computing cluster, have already been mentioned twice. So some of the topics that we covered today, especially in the morning, they're very useful when you really need to scale your analysis, that you need kind of, parallel computers, parallel processes to analyze large amount of data. So what you see right now on the screen are the notes document. Just have received an email from me with this link. If Johan could just scroll down a little bit, I left there the feedback from yesterday. So you can still, if you didn't have time to write something yesterday, something nice, and of course, something also that could be improved. As you might have noticed, we are trying to improve as fast as we can based on your feedback. But if you scroll a little bit more down, there's a couple of icebreaker questions for today. And I'm gonna ask the second question, starting from Susa. So what's the most surprising thing you have learned in your career?
I think the most surprising thing that I've learned in my career, keeps surprising me, is how difficult it is, or how scary it is to share your code, like put it on GitHub and um have other people see it. I mean, everyone struggles with this, and everyone has unclean, not so nice looking code, but still people think, no, it's only my code that looks so bad. And I get that sometimes myself. I think this isn't good code, really. Do I really want to show it to someone? But yeah.
Especially like I work with many RSCs, so many people who share their code, and it never came to my mind to read their code in a way like, look, I would have not written this variable name in that way, or things like that. So in the end, it doesn't really matter. But it's true, maybe we are more self-critical than like critical towards others. It never happened to me that I have to give comments to one of you on your. And so same question for Johan. What's the most surprising thing you've learned in your career?
Yes, so one thing is this we talk about sometimes also in this code refinery workshop about this, that when the aspect of reproducibility in science, it can often, one aspect is this, that sometimes the person that is to reproduce can be yourself. And that has led to some comical situations where I have been running some simulations with some program, and after a few days I realized, oh, this seems very familiar. And what then has happened is that I simply been running something that I ran, let's say, a half years ago. It's just that I had it somewhere else in my file system hierarchy, and I didn't have like the I'd forgotten simply that I've done it. So yeah, I find that quite interesting.
I agree. I wouldn't call it a daily struggle, but sometimes even remembering which subfolder was I using when I was running that analysis. And what about you, Lauri? What's some surprising thing you learned?
Yeah, so this is definitely not the most surprising because I couldn't think of a better one since I don't have 10 minutes to think about this. But so one thing that's also relevant for today is that I'm always surprised how much Python is actually used in high performance supercomputing environment. And it also makes sense if you think about the needs of today's kind of computing clusters, because a lot of the work is actually offloaded to GPUs, and Python is just doing the kind of CPU side logic that tells what the GPU should do. And in that sense, it makes perfect sense that Python is now a very good language, actually. Despite the Python being inherently slow, it doesn't really matter if the GPU is doing most of the workloads. So
Yeah,
that was something that I'm still quite impressed by and also surprised by. And I think this will actually become even more common in the future.
I agree. And what you said just connects perfectly with the topic of the morning, where under the Python hood there is C and C++ and or CUDA. There are other languages that are called to gain the speed. You kind of saw this already when we were mentioning when we were talking about NumPy and XArray, how under the hood, it's not just pure Python. Well, we still have a couple of minutes. Maybe I can answer the icebreaker myself. What's the most surprising thing I've learned in my career? And I think it's what I wrote there first, planning ahead. And planning ahead can mean, not just when you start a project, you have a long-term plan for the project, but even when you start a script, I usually start from writing the comments. I just write all the comments down so that I know first I need to do this, then I need to, I don't know, pre-process what I loaded and so on. And after I've written all the comments, then I actually start writing the code, filling in the missing bits. It makes it much easier, and especially if you get interrupted, what you were doing and what you were thinking. And sometimes even pen and paper or pencil and paper, it's even the best to start planning a script. But yes, so we still have 1 minute before starting. I can see that people are already editing this notes document. Anything else you want to add? Susa, Johan, Lauri? Nothing comes to mind. So maybe I can briefly say that this is our last day together. You've been very active. We have now 500 people registered, so 500 round number. And you will still have more days for going through the videos. And for those of you who want the credit, do the simple homeworks. And in general, if you have questions, you can always reach out so that we can answer your questions and hopefully improve this course for next year. There were already good suggestions there in the top. Someone was asking for an extra hour every day. So maybe next year it will be 5 hours per day course. But otherwise, it's now 10 o'clock in Helsinki, so we can actually start. Welcome to the third and last day of this run of Python for scientific computing. Today, for day 3, we will cover kind of a little bit more advanced topics compared to the previous 2 days. Or well, I'm not sure if they should be called advanced, but at least they relate to those cases when the analysis need to scale up a lot. So in the morning, we will talk about parallel programming and Cython, which is basically what's under the hood of the Python scripts that you might be running. And in the afternoon, we will cover packaging. So when you want to create your own library, when you want to reuse your code easily. And of course, something that you have already experienced, when you need to install all the right versions of Python libraries, which is dependency management. Just a quick reminder for asking questions, we use this notes document that we see right now on screen. So Johan, if you can scroll up to the very top. you see that there's a pencil on top. When you click on the pencil, the document turns into an editor, and then you're able to write something. So for example, Johan, you can scroll to the very bottom and tell us what would be your favorite winter holiday activity. For me, it was sleep.
Yeah, one thing I hope to do this coming weekend is to go ice skating
Okay, that's nice.
on a lake nearby.
Okay, so it's already frozen enough, safely enough frozen.
Yes, 1 decimeter already.
Wow. Here in Finland, I wouldn't yet try to go skate on a lake, at least not here in the Helsinki. But so you got the idea. If you don't need this document, there is another icon in the top, which is the eye, so that we can basically get less load on the server that is hosting this. And final reminder, when you look at the TwitchTV stream, please set the quality to source. Otherwise, at some point, you will start seeing big pixels, and that's not nice. But that's enough with me talking. So I'm happy to pass the stage to Susa and Johan. Enjoy the last day of Python for Scientific Computing and see you later.
Yes. Hello from me as well. Thanks for joining us again. We are going to start by talking about parallel programming. So maybe to get started, what is parallelism? What is parallel programming, and why and when should I be using it, Johan?
Yes. So to start with a bit of an historical account. So in the history of computing, the early computers were essentially serial. So it was the processors would run one execution thread, and that was it. And probably many of you have seen these graphs where you show the evolution of hardware over multiple decades. And this started to flatten out as regards clock frequency around 20 years ago, when we reached around 3 gigahertz. So essentially, most of the speed up which has happened since then is in form of running things not faster per execution thread, but to run them in parallel. And parallel nowadays often is in multiple execution threads on one single chip. And this affects very much how you write programs and how you execute programs. And Python has its own way of doing it, and this is the topic for this morning. So one of the first things that you need to do when you have a demanding computation is that you need to find where is the program spending most of the time. So where do you have, so to say, a good opening for redesigning it? So do you have any experience of doing that, Susa?
Sorry.
Yeah, I was thinking, have you analyzed a program to see where it spends time?
Well, yes. Well, actually, I was just teaching about profiling code yesterday together with Simo. So what I used in the past is to use Glean. Thing is, the most important bit about profiling is you need to know whether you want to profile. So you want to see whether your program spends more time than it should, or than you can afford, really. And then you want to see where it spends that time, and you can use a profiler for that, as we talked about yesterday. Or maybe you want to use you want to look at how much memory it uses, but I think for the parallelism, it's mostly the time that you can speed up with it going parallel, right? I mean, you can't really do much about the memory consumption. Or can you actually? What do you think?
Well, that depends in part in what kind of parallelism that you implement. So actually that comes here. We can highlight what you have here in the lesson material. So some different modes of parallelism. So there's one concept which is called embarrassingly parallel, and that is when you have a compute workflow where you need to run multiple instances of a calculation or an analysis. Let's say you have 200 data sets and you have them in form of 200 files. Then you can write a script that just loops over this whole set of files, and everything is then run in parallel, and it needs not to be synchronous.
Yeah, that's something that happens. So I'm from neuroimaging originally, and this is something that happens so often in neuroimaging. Like you have 50 subjects and you need to pre-process them all, but they are not really, they don't depend on each other. So you can just show that off to 50 different computers if you have the amount of computers.
Yes. And here, coming here to when you want to do things a little bit in parallel for one single calculation, then we have the concept of multi-threading, and that is where you are. It's a thread memory mode parallelism, where you let multiple threads in the execution of your program work in parallel on the data. And as we will see here later.
So hang on. What's a thread here?
A thread is so logically in the execution of the program is it's doing something sequentially, and you can then typically have up to as many threads as you have physical cores in the processor. That's a typical thing that you would like to have. In Python, however, what is more natural to use is so-called multiprocessing, and that is when you launch multiple instances of the program execution, and they will then work with their own memory segments. And that means that one such process cannot automatically access the memory of the other processes, so you need then to have some communications going in between there. And this is called message passing. And one important protocol for this is the so-called MPI, message passing interface, which is a bit more than 30 years old. And here in Python, we will work with a package which is called multiprocessing. So I think we'll make here first a little bit a notion here about multi-threading, and then we will come into multiprocessing. So by design in Python, there is something which is called the global interpreter lock, GIL, and that restricts the program execution to use only one thread at a time. And one could say that this is possibly a limitation. However, in practice, it's so that if you invoke some library underneath, that can be then libraries such as NumPy, SciPy, or Pandas that you have encountered earlier in this course. They're written in C language, and within them, this lock can be released so you can run multiple threads. And it's also so that if you link your program to some other library, that could be then, for instance, some LAPACK libraries for linear algebra, which is external completely to Python, then also there you can run things in parallel. So we will here make just to showcase here how this is working with a code snippet here from NumPy. We can take this code here that will invert a symmetrical matrix. And this code here is using NumPy. So we set up a random matrix A, which is sized 4000 by 4000, and use then the NumPy invert function to invert it. So I take this code snippet here, and I put it in my Jupyter notebook. And okay, actually this I could run in the terminal, so I do that instead. Yes, I already have the code here, and run it. That was 3.79 seconds.
But that is with multiple threads, right? Because NumPy uses C in the background
Yes,
and
exactly.
uses multiple threads. So what happens if you turn the multi-threading off, basically?
Yes, we can do some experiment here. So here I'm okay, it actually by default it uses one thread, and now I increase it to use, say, 4 threads. You see, and this is something, yeah, now it cut the time with a factor of 2. Potentially it could have cut the time with a factor as large as 4, but here it achieved only a speed up of 2.
Why is that? What do you think?
So in general, parallelism, the speed up is typically the ideal speed up will be if you increase the amount of hardware available with a factor of X, then the tentative speed up you could foresee is up to a factor of X. So in this time a factor of 4. So that is also the natural target when you implement and optimize parallel code. You would like to strive to come as close up to that so-called ideal scaling as possible. But for many reasons, this can be more or less challenging to achieve. One reason why it sometimes is slow can simply be that the calculation that you want to perform is a little bit small. So then there's not enough workload to distribute. So then simply going to larger workloads, you will for that reason achieve better performance.
Or invertedly, if you just have that small workload, it doesn't pay to add the additional threads to it.
Yes.
Because usually you have a problem that you want to solve and you don't necessarily, you can't necessarily scale it up infinitely to make it more sensible to use multiple threads or multiple processes.
Yes, indeed. So we will now come to a main functionality for parallelism in Python, which is the so-called multiprocessing flow. And we have an example of how to do that for a simple mathematical function here, which is calculating the square of a number. So we have here the definition of this function here. It's defined as a square that takes an input argument x and returns its square. If you want to, I mean, you can use the map function here to apply the square function to every element in the list. If you invoke the square function with, nested in with map. If you execute this snippet here, things will be done in serial. If we use this here so-called multiprocessing packet, we imported the pool function. Then we can use pool, and then we distribute the calls to the square function over the set of elements here in this list. And this will then be run in parallel. This here is still a very small program. So for this very example here, we have only 6 elements in the list. There will not be any, this is quasi-instantaneous in any case, so there's not much to parallelize here. So one important thing here, because we're primarily using Jupyter notebooks here, is that this multiprocessing packets might not always work in Jupyter Notebook, but then there's a fork of this, which is called multiprocess, that one can run instead. So you will now have, in an exercise that we will get going to in a minute, have the chance to explore the functionality of multiprocessing. So we can introduce what this exercise is about. So perhaps if someone can share the direct link here to the exercise in the collaborative document. So the code snippet here is a method called sample, which is calculating an approximation to pi. And it's doing this with a Monte Carlo algorithm when it is generating random numbers within a square. And then there's an if statement that checks, do these random numbers fall within a circle which is inscribed within this square. And this suits itself very naturally to parallelism. So for this exercise, you will then, so this code in here is serial. And what you will explore here is how you can speed this up by using the multiprocessing pool functionality. So, Susa, are there any more instructions that we could mention?
No, basically, I think, well, the exercise description is in the exercise. You will have 10 minutes to explore this exercise.
Mm-hmm.
And then, yeah, we'll put a link also to the exercise in the notes document.
Yes. Good. So,
And then, so it's basically 20 parts now, so exercise will be until past. Also add that.
Good. So see you in 10 minutes.
Okay, I think we are back. So welcome back.
I think the sharing is probably not correct.
Yeah, I think you're at the moment, unfortunately, seeing
Yeah, well, you can see my notes.
a little more than you should be seeing, but
Yeah,
but instead you can't read anything. We'll try to fix that soon.
all right. It's starting to look better.
It's becoming bigger now.
Yeah, okay. Good, good. And this should be readable, I hope.
Yeah. All right.
All right.
So we saw some very nice discussion in the notes during the exercise. I hope you got on with the exercise all right.
Yeah, there were some good questions here about the latest version of Python, and I mean the release of the global interpreter lock, which is now implemented. And that's a good thing to bring up. And I have so Lauri, have you explored this newest version of?
Right. So we discussed this a bit over the exercise session in the private room also, but we don't have direct experience with this new Python version that does not use the GIL global interpreter lock. But in principle, it is there in the standard now. It should be working. But I personally would be a bit cautious about using it or building your application with the assumption that you can now ignore the GIL completely because it's just such a new feature. So I think it's a promising new feature, but maybe not for production yet, just yet. And one thing about the GIL in general is that it's very easy to bypass if you write the code that does multi-threading in some other language and then bind it to Python, which will be discussed in a moment in more detail.
Yeah. Someone on the notes highlighted that in the exercise, running it with multiprocessing is actually slower. And yeah, it is, because what we're doing there is we're kind of misusing it a bit. It's a pure Python code, and it's a relatively small example. So adding the so when you're adding threads or multiple processes, what you're doing is you're telling your computer to create different processes, but these processes all need to be handled. And that means you're adding overhead. The computer needs to do more to do the same thing. And because it's a relatively small example and it's code that doesn't really like multiple threads, multiple processings, it's actually the overhead that you're adding is more than the time gain you get. So in the end, it is slower. What we, I think, show with this is that it doesn't always make sense to go to complicated multiple tool kind of things if your problem actually is easier to solve in other ways. One of them is the embarrassingly parallel case, well, this is something that I come across all the time in neuroimaging. If you can separate the problems, you don't have to handle pools, you don't have to handle the overhead. You just run your program for each instance separately. That is an easy speed up without adding overhead. So yeah, that's, I think, the point of this exercise.
Yeah, and I should add that if you can do it in a way that's embarrassingly parallel, so you're just running independent processes, then that's always the best option because there are no overhead associated with kind of spawning threads or spawning multiple processes within one process. But of course, that's always not possible. And should we move on to MPI already? Or is
Yeah,
there
I
something
think
else you want to say about this?
no, I think we're good. There wasn't
Okay.
anything else in the notes specifically to the exercise. And we will keep answering questions in the notes as usual.
Yes, so let's talk about MPI. So as mentioned already, MPI stands for Message Passing Interface. It's a kind of protocol or a standard that allows you to launch multiple processes that can also communicate with each other. And this is very useful if you want to say utilize a large computing cluster, because you can launch one large job with MPI, which essentially then launches many copies of a program, and then those can start communicating with each other, so that you can implement things like divide a large simulation into smaller simulations that then communicate just the data that they need to communicate between each other. And this is the main method or main way that most scientific simulation programs scale themselves so that they can run on, let's say, extreme case, full supercomputer just running one simulation. So this is a very typical approach in high performance computing. So what MPI does is that you run a command called MPI exec or MPI run, and that will take care of spawning the processes. And it will also assign a unique integer number called the rank to each process. And of course, the operating system will usually assign these processes so that each process runs in an independent CPU core, so that it's like you get the max possible performance. There's no competition of resources within one within the processes, assuming you have a large enough computer, of course. And yes.
No, yeah, just a comment. So sometimes it's also perfectly fine to run more ranks than you have physical cores. And that could be also depending on what algorithm you have. So perhaps it is so that algorithmically you would like to run, let's say, as many as 4,000 ranks of a program of the program, simply because your problem size is that large. And you might then not have that many cores available. Then you can have less run with this many large number of ranks.
Yeah, and just to reiterate, MPI is a form of multiprocessing, but it differs from Python's this built-in multiprocessing package by the fact that you can actually communicate between the processes. And the MPI is also implemented usually in C or Fortran. And then this Python implementation that we're looking at today is a thin wrapper around the C implementation. So yeah, the communication between processes is the main part here. And this is not multi-threading. So the big difference with multi-threading is, of course, that the memory space of each process is independent. There's no shared memory like that. But you can actually combine MPI with multi-threading so that inside an MPI process, those processes will then launch multiple threads and do multi-threading that way, which is also quite common in real-world applications. Okay, so I thought that we could do a short demo of just doing a hello world printing in MPI. So let's try to do that. So here I have an empty Python file called MPI demo, and I will write the code here in my editor. And the reason I'm not doing this inside Jupyter is that I'm really not sure how well Jupyter handles the spawning of multiple MPI processes. So I'm going to do this the traditional way. Okay, so we're going to start by importing from the MPI for Py package And now I need to cheat. Is it capital or not? It's not capital. Okay. MPI for pi, import MPI. And yeah, here's the example code. I'm going to copy parts of this that you see in the browser. Let's just start by printing a string from each process that MPI launches. So for that, we need to know or we don't need, but I want to print the ranks, the identifiers that MPI assigns to the processes. So I'm going to get the rank of my processes. So I do this by first getting what is called a communicator. So communicator in MPI is an object that contains information about a group of processes and how they can communicate between each other. And world communicator in particular refers to all processes started by this MPI started command, which I'll show in a moment. But anyway, let's get the word communicator. Looks like this. And by the way, this is very similar in C or Fortran if you've already used MPI there. But because this is Python, so it's slightly shorter, which is nice. So we can ask for a property called size. Size refers to the number of processes that were launched. And then the rank is the identifier of my process, like this. And now if I run this code with MPI, then remember that all the processes will execute this, but what the number they get out from this rank is different because MPI just gives a unique identifier to each process. And let's print that out to see it in action. Hello world from rank or process. Let's call it task, MPI task, rank. All right, and now I'm going to go to my terminal, go to the right directory. And the way to start an MPI program, at least on your laptop, is to use the MPI exec or MPI run command. On supercomputers, this can be different because they have their own task managers, job systems, whatever, like Slurm uses srun. But you can find that in the user manual of your supercomputer. So that's always something to check on case by case basis. But yes, let's run two processes. And the file is called mpidemo.py. And now we get two prints, and you can see that the rank or the task number is different. And just for comparison, if I run this without MPI, like just Python usual thingy, they will just have one process. And the magic argument n here is the number of processes that is going to be spawned by MPI. So I can do 4, and now I get 4 prints. I can do it again just to illustrate one thing, which is that the order of these prints is not deterministic. You can see the order is different. And this is because the execution, there's kind of a race in which process gets to do the first printing. And that's the order you end up seeing here. So just something to keep in mind if you print out stuff into standard output from MPI. Now, my laptop has 6 CPU cores, if I remember right. So I can do this, which is still fine. So every process gets now a unique CPU core to work with. So there's no competition of resources. Of course, in this example, it doesn't really matter because this runs instantly. But I can also do, let's say, 12, which hopefully runs. Yes. It runs, but now it means that there are 2 processes per 1 CPU core, which is not ideal in a real computing environment.
Yeah, and
Yes.
as we, at least I noticed that it took quite a bit longer until it started printing things. So that's probably the overhead from having to switch
It could
tasks
be,
on the same
but
core.
yeah.
Might be,
But
anyway.
it's hard to say because this runs so fast. So
Indeed. But
we will need the proper action. Let's do 100. Yeah, now it's taking long to even start.
yeah, because it doesn't know what it's supposed to do first. It needs to decide that.
Yeah, but this still runs. Some MPI implementations may not even allow you to start the program if there are not enough cores to kind of have running independently. I guess it depends also on how it's configured. But anyway, here it does work.
Yeah, that's a good point. So indeed, that can be dependent on the configuration and on supercomputers, which I mean they're shared between many users. Then typically the setting is that it is not possible to overscribe the physical cores. But you will get a clean error message then if you try to do that.
Yes. So now should we move on to the exercise? And the exercise is doing the same thing as with multiprocessing, which is calculating pi, but now do it with MPI instead. And the main difference is going to be that there's communication between the processes. There's what's called collective communication. So every process participates to communicate some data. So message in MPI means some data always. So you're sending numbers between processes or bytes to be specific. So the exercise is here. Do we have any comments before we start?
We don't have any new comments on the note stocks. I don't think we have, at least from my side, I don't have any comments. I think we planned 15 minutes for this exercise. And after that, since it's already 47, let's make it exercise until the full hour, and then we will have a break of 10 minutes.
All right, sounds good.
Add to the notes document. So see you again in, well, 25 minutes. Don't forget to actually take your break and get up and stretch a little. And well, with that, bye and see you later.
See you in a bit. Hello everyone, welcome back. So I hope you managed to do something at least with this exercise. Now from reading the notes, there have been some installation issues regarding MPI, which is completely understandable because installing MPI or using MPI libraries is not always entirely trivial. And the reason in this case is that even if you download MPI for Py, the Python package with, let's say, pip, then you may still not get the actual MPI runtime library needed to use it. And this is on purpose because you usually don't want to download just any implementation of MPI. You want to use the one that's been configured and made available on your HPC system. But now, of course, if you're doing this on your own laptop, it would be nice to have it available. And the solution for that is to use the Conda environment, which is really the recommended way for this course here, because it turns out that Conda is able to download a working MPI runtime library for you. It may not be the most optimal one, but just for running things on your laptop, it doesn't necessarily need to be the most optimal version available. So in short, if you had issues using MPI, try doing this in the Conda environment as instructed on the course page. All right, so now do the actual exercise and let's look at the solution. Actually, before that, let me run it a few times. So I have the exercise code here, just the same code copied from the page. And now I'm going to run it a few times to see what the output should look like. So MPI exec number of processes, let's start with 1. So no parallelization whatsoever. And the file is called MPI exercise.py.
So I notice here that in the Python code that you have increased n to 10 raised to 8. So
let's try again.
Yeah.
Yeah, sorry, I had increased the number of tries that the program, or number of random numbers that it generates. I had increased it by order of magnitude for testing. So now it's back to 7, which is on the example. So now we get that it through this many darts, so 10 to 7, it gets an estimate for pi, which looks pretty good. And the time spent was 2.5 seconds. And now just to compare, let's do 2 processes. And we expect the speed up to be roughly 2 times. 1.4. It's not exactly 2 times faster because of, well, this is just measuring it once, so there's deviation. And the other reason is that communications are overhead, always in MPI. And in this case, so what is going on is that it's running this function many times in, well, this many times generating these 2 random numbers and then checking if you end up inside a circle. And it's doing this now in each process independently. And then in the end, there is something called a gather. So gather operation in MPI means that we're gathering data from all processes inside the communicator to one process. And the one process is called the root process of the gather. And here we specify root 0. So we're gathering to the process whose rank is 0. And then it calculates the usual sum of this to estimate the pi. And there's also if statement for checking if the rank is 0. And if yes, then it does this summation and prints the pi. And this is because we don't want to print this thing out from all processes. We could, but it's redundant. And the corresponding prints are, well, there is the final print showing the result and the timing. And then there's these two kind of testing demonstration prints that show the number of hits inside the circle before and after gather. And now, interesting, you can see that in, let's say rank 0, after gather, the data array is actually really an array here. It has 2 elements, and these are gathered from the 2 processes. This is just the number of hits in the original rank 0 process, which is just gets gathered like this. And the other number is from the other process, gets gathered here. And after the gather process, in the process that's not the root process, there's no data left. So gather kind of removes the data in that case. And we can repeat this with other processes as well, other number of processes. So now with 4 processes, it's again faster. It's not faster by a factor of 2, but close enough. And let's do 6 as well. Yeah. Now this time the speed up was a bit less impressive. Final demonstration. What happens if I make this run this with many processes, like way more processes than I have CPU resources on my laptop? Then we expect it to be slow. So let's try 20. And this should be much slower than running let's say 6 processes. Yeah, 0.8 seconds, which was slower than with the 6 processes. It's because there's no competition between CPU resources or competition of CPU resources among these processes. Okay. And again, there was also a question about why is the order of prints kind of random, and it's just because MPI starts as many processes as you tell it to, and then each of those processes will execute independently, and the kind of actual speed at which they execute it may not be the same for all the processes because of things like operating system assigning resources to other processes also on the operating system. So that's just how it goes. It's not deterministic.
Yeah, and that's it is like that also for efficiency, because if you would have it deterministic, then you would need to somehow implement, or the operating system would need to monitor then that, okay, first rank 0 does its thing, then rank 1, and then rank 3, and so forth. And every now and in an MPI program, you need to have this kind of either like things that are sequential, or you need to do some kind of synchronization. But this also costs a little bit of time, because then the rank switches are perhaps finished with their tasks. They need then to wait for the other ranks.
Yes, that's a very good point, that we can enforce the order of things that happen in MPI by using synchronization. There's a function called MPI barrier, for example, which synchronizes everything in the communicator. But that is usually not what you want to do, because then that means that all the processes would have to wait until everyone, like all the other processes also are at the same point of execution. So that's in most cases that's unnecessary waiting. But of course, in some cases you just have to synchronize depending on your algorithm, on what you're computing.
Yes, indeed. And an example here in this particular code is that towards the very end here, you need to add up the individual contributions from each and every rank here before you then get the best possible approximate for pi here, which is to combine from all of them.
Yes, so indeed we cannot really proceed beyond this gather function call until all the processes have actually finished their computations and have sent their results to the root node. So there is actually an implicit synchronization here in this gather call.
Yes.
Okay. Any other comments or questions about MPI? Susan, maybe.
I'm just trying to look whether there's anything in the notes that is that we should discuss, but I don't see anything. Well, people have been problems with MPI not being there. I think this is something that happens quite commonly, that you have it might be working on the one system, but then on a different system, because the MPI needs some other installation steps, it won't be working on that system with the same sort of installation script, especially common when switching from Windows to Linux or vice versa. And yes, that's unfortunately, because MPI is relatively close to the hardware, it's kind of unavoidable, isn't it?
Yeah, and I think for Windows in particular, MPI is not, let's say, it's not very relevant for Windows because there are no supercomputers running Windows these days. So it's really like implementing and maintaining MPI for Windows systems is not something Microsoft is putting tons of resources into. MPI is it's mostly just a kind of high performance computing library. It's not used really outside HPC.
Yeah.
But so I said that, but I need to say that it's used very like a lot in HPC. Like all the supercomputers have some MPI implementation available. It's the main method of parallelization in modern clusters, modern supercomputers, and it's also where a lot of kind of technical issues show up, because I mean MPI has to kind of communicate. It has to work across a full supercomputer, which supercomputers are essentially many smaller computers linked together. And MPI is one software side thing that kind of lets this linking to be possible for users. And if something breaks, it's very often actually MPI, at least from my experience. Which is also why supercomputers are, like, often they have a one recommended MPI library that you should use on that system, and meaning that do not use the MPI that you would download from let's say, I don't know, pip or something like that. Try to use the system MPI as much as possible if it's available.
There's actually an interesting question in the notes document, asking if you're forced to use Windows because your company or university wants you to, does it make sense to work on VSL, it's Windows subsystem for Linux, i.e. running Linux on a Windows machine, for the people who didn't know, if you want to go to supercomputing, or like if you want to run your code on a cluster later on? What do you think, Lauri?
So I think so here I'm assuming that the cluster or supercomputer itself will not be Windows, so it will be some Linux
Well,
computer like they
as
always
you
are.
just said, I don't think there are any actually
Yeah,
Windows
but
supercomputers.
for developing and testing your code on a Windows system, then using, let's say, this Linux subsystem for Windows is perfect with MPI is a perfectly valid approach. Anything that lets you compile your code, run your code, and test it with if it needs MPI, then great, even on Windows.
Yeah, Windows subsystem for Linux is overall very stable. So there's still, I mean, after all, it's not native Linux, but it has almost everything is in place. So yeah, I could recommend it, and I also have some own experience from running it, and including also running with MPI, and that works nice on the one machine where I've tried it.
Great.
Yeah, and final comment on MPI is that usually you will know if your program should or would benefit from MPI. It's when you need to really, you have complicated, let's say, parallelization needs, and you need to pass messages around, pass data around, things like this. And if you're simulating anything that needs to scale up to very large node counts, CPU counts, then usually MPI is the way to go. But the other side is that if you don't need MPI, then don't force your program to use it. Because if you can do it in an impartially parallel way, then that's even better, because then there's no communication overhead. Okay, I think we should move on. The next topic is a short discussion of coupling Python with other languages. And this is something that I will discuss more in detail in the next episode, which is on Python. But just to give a very short overview of what's in this section, is that there are, let's say, three main reasons you may want to combine Python with other programming languages like C, Fortran, C++, things that either run faster or are convenient for other reasons. The reason something like C may be more convenient than Python is that it doesn't have the global interpreter lock. So you can do multi-threading there without worrying about this kill in Python. The other reason might be that you have there's a library implemented in, let's say, C, and you want to call that library from Python. So what you do is that you usually write a thin wrapper code that exposes this library to Python, and this is called extending Python with usually C. The third reason that I want to mention is that sometimes Python is just too slow to execute some particular algorithm that you need to do. Like you have some specific computation, it doesn't really work well in Python because Python is inherently a slow language. Then what you can do is you write just that part in a faster language and then expose it to Python so that you can still have your main program written in Python. You just call that function that's now written in another language. You call that from your main Python program. And this is very common in scientific codes. How do you actually do this? Well, there are good libraries for handling this, for handling the, let's say, most of the painful stuff for you. Just to pick a few or highlight a few, there's a package called CFFI, which lets you expose C code to Python or vice versa. There's also C types, which is built into the Python standard library. It's similar to CFFI, but it's a bit more, let's say, elementary, has less features. For C++, there's a very good library called PyBind11, but it is really just for C++, it doesn't work in C. For Fortran, you can, what you usually do is you would expose first to C, expose your Fortran first to C, and then expose that C code to Python, so there's a kind of two-way process there. And then for us, there's also a library called PyO. 3. Rust is not very popular in scientific codes yet, at least not yet. Maybe it will be in the future. And the point here is that these are all faster languages that do not suffer from kind of this slowness that's inherent to Python, which is an interpreted language. More on that in just a few minutes.
So I could add on here. So you mentioned many reasons why you would like to combine languages, and many of them have to do with performance. Another aspect naturally is when it comes to different features and functionality. So for scientific code, it's very common that you get some kind of numerical output or raw output that you would further like to analyze or visualize. And if you have the bindings to that program and to Python, you can then get going with I'm using matplotlib or you can work with pandas, you can or work with any of the other visualization packages. That can be very powerful.
Yeah. Then just a very brief comment that there are also many other libraries that can do kind of parallel computations inside Python. Dask, for example, is something that you can use for dividing a NumPy array work or kind of array-like work to many processes. It's a Python library. You can have a look at it if it sounds interesting. It will chunk the array into smaller parts and divide those parts to many processes then. Then there are something called task queues, and these are essentially helper programs for launching multiple processes. Might be a bit redundant in actual supercomputing environments because they usually have their own job systems for doing these kind of things. But if you're interested, there's a link, you can have a look. Right. So the next topic would be Python, which is an example of actually combining Python with C code. But before we get into that, do we have any final comments about this section?
We could highlight that we have added a few examples of scientific codes that combine Python with C++, as well as with queued and heap code for running on GPUs. So there's one link here to the numerical toolkit Runco for simulating astrophysical plasmas. And then there's also a code VeloxChem for quantum chemistry. And for the latter, I know from the developers that they use very much a workflow and modality of using the code based on Jupyter notebooks, and that scales then very well. So they can run. You can run on your own laptop to poke around, and you could use it for teaching and demonstrations, and still staying on the laptop. But you can then offload. If you have bigger calculations, you can then offload it to the supercomputer. So that's I mean, not least for the context of teaching chemistry here, I've heard that it's been rather successful because then you can showcase and let the students make use of the code which is run for the really heavy calculations. So it's the real tool, so to say.
Yeah, Python is very commonly used as a kind of glue to stitch many packages written in other languages together, and Python is very good at that.
Yeah, indeed.
Okay, but now in the interest of time,
Yeah,
I
would
think
maybe
we should move on.
quickly, as a summary, add that hopefully we've shown you today in this lesson that parallel programming is a tool. It's not always the tool you need, even if your code is running slightly slower than you would like it. Profile it first. See if you can speed it up in other ways first, and if you cannot speed it up in other ways, then it is the time to look at parallel programming, and we've shown you a few ways to do it. So then we'll discuss it, think a bit more about using other languages than Python to do actual baseline parallel things. And yeah, that's about what I wanted to summarize. And I'll say goodbye for now from this time.
Okay, so I'll also leave now. So thank you and goodbye.
Thanks. Okay, so we are a bit behind the schedule because I've been rambling so much. But so Ashwin is now joining me for the next section, next topic, which is Python. So this is in the section called extending Python with Python here on the course page. We're going to discuss one quite popular approach for combining Python with C code and also improving performance of it. Let me get rid of the sidebar real quick.
Exactly. So
Yeah, okay.
hello, everyone. So yes,
Hello.
Python can be slow, as Laurie rightfully put it, and Python is one possible approach to compile and make performance benefits. Yeah. So Laurie, what is Python? Like, how does it do things?
Python is well, it's a Python package, and it's also kind of tool for producing C code from Python code and compiling that using a standard C compiler, so that the generated code has all the necessary boilerplate that Python needs in order to call this a compiled code from Python. So Python is one way of doing that. And now the real selling point of Python is that it allows you to add static type declarations to your code, which can drastically speed the execution, because Python doesn't need to then interpret the types all the time.
Right.
And so maybe we should actually discuss that, because I have here an example of why exactly is Python slow in, let's say, most cases.
Yeah.
And the reason is that Python is a strongly typed language, and it's also dynamically typed language. What this means, that the strongly typed means that all variables have a type, and this type is important for what operations can be performed on that variable. So the type needs to be known in order to do anything with the variable. And Python will figure this out, or figure this type out at runtime and check it all the time. And this is the part about dynamic typing. So the type can change at runtime. And so just an example, what actually happens, or what Python needs to do in order to add two integers in this example here. Let's say we're adding 7 to 6, and variable names are A and B. Then what happens on this line is that Python needs to do what's called unboxing of variables, or unboxing of the type. So it needs to check first that, okay, we have an integer. Sorry, we have variable called A, and now let's check the type. Okay, the type is an integer. So that takes time to do that check. And everything, just to reiterate, everything is an object, even integers. They just have a number associated with them, but they have other data as well, as shown in this box here. Now the same thing for the other variable. We have variable B. Okay, it's an integer. And now the next thing it checks is that, okay, is there an operation implemented for this called addition, that with this addition symbol? So Python has to check that. also. And then it finds that, okay, yes, integers can be added together. Now let's do the actual addition. And this is where it would then call something on some addition routine on the CPU. But that's not everything, because then it needs to put the types back in the result. So it gets a result, it's number 13, but in order to pass this number back to Python, it needs to do boxing of the variable type. So that also takes time. It creates a new Python object that's of the integer type. And this happens all the time in Python. And a large part of why Python really is a slow language is because of this kind of boxing and unboxing of variables. The other reason Python is slow has to do with interpreting itself, because it's an interpreted language.
But Lauri, is this always the case? Do we have examples like NumPy where this is circumvented? This
Yes,
boxing and
very good. Very good. NumPy, what happens when you call some function on NumPy array from NumPy is that it actually calls a C function where the routine is implemented in a faster compiled language like C or Fortran, usually, in the case of NumPy, actually.
right.
So in that case, because the types are known for NumPy arrays, the arrays have only one fixed type. They're either integers, they're either floating point numbers, or something else that is known. So NumPy can do very fast operations on that. So the speed is going to be similar to compiled language like C or Fortran.
So it's actually like certain libraries actually makes use of this compiler, which is Python, to enhance their performance.
Yeah.
And
so sorry, so NumPy
right.
doesn't actually use Python as very much, as far as I know.
Maybe
but
SciPy does, at least. I think so.
QPy didn't.
SciPy.
SciPy maybe does. I don't know.
Yeah.
I know the QPy, which is a kind of GPU version of NumPy. That's all written in Python.
Okay. So then we know like what performance pitfalls you can have. At least one of them is this unboxing.
Yes.
And how do we? Maybe we can mention that this episode is also going to be a demo, so we don't expect everyone to follow along. So sit back.
Yes. So indeed, because we will be compiling C code here, and
Right.
having that kind of working compilation environment for that goes beyond what is required for this course. So we don't really have exercises here, and we will be demoing this. You can follow along if you want. You can try running this command here in your conda environment. It will install Python, and it will attempt to get the C compiler as well, if you don't have one already. All right, so now we established that Python is indeed a slow language. So it's not just a joke that Python is slow, it's actually slow. But the good thing is that in many cases, like many libraries that we use in Python, they actually written in a faster language under the hood. So the slowness is not as big of a deal. Except that if you have your own code that needs to do something that NumPy is not good at, for example, code that doesn't vectorize well, then you may have to write this your own code in a faster language and then export that to Python. And this is called kind of writing Python extension modules. And usually it's done in C. There are many ways of doing this. You can use some of those libraries described in the earlier section. And these are very useful if you already have a working C code or Fortran code or C++ code. If you don't, then this is where Python comes in. So Python is a way of writing Python-like code, but that also can be compiled to C code, and you can optimize it by adding static type declarations. So Python extends the Python language with a bit more new stuff that can be useful for optimizing.
So if I understood correctly, you don't have to learn C to create extensions. we can stay with the Python-like syntax and still generate extensions, right?
Yes, and we can demonstrate this.
Yes.
So let's look at the demo here. Your first Python module, and I should actually open my code editor and open a new file here. So I'm going to create a file called mymodule.py. Just let's start with the normal Python module. And I'm going to add a function that just adds 2 numbers. Very simple.
Yeah.
So it will take in what are assumed to be numbers, x and y, and add them together and then return the result.
Mm.
So that's the module. And now you know how to use this from Python. You import this into another Python module and call the function from there. But with Python, what we can do is we use a command line tool called Pythonize to compile it. So this will compile the code and do it in place. So this -i means in place, and it will produce what's called a Python extension module. It's a compiled binary containing this function that we have.
Okay.
And so what happened is that we have the original module here.
Mm.
Then we have a C code, like file containing C code. And let's actually have a quick look at it, although it's not pretty. So this is what Python generated from our Python function. It's a long file with a lot of kind of Python API usage, and it's not very readable.
Mm.
It's mostly just preprocessor stuff. And it has, well, the line numbers are not visible here, but it has almost 8,000 lines just for adding 2 numbers. So point being, these are not meant to be human readable, but it's valid C code that a C compiler can then compile for you. And the compilation was done by Python when I run this Pythonize-i command. It produced a file called mymodule.cpython something something something.so. So so means it's a shared library. And this is called the Python extension module. It contains the compiled version of our function, and we can import this to Python. So let me demonstrate. I can do from my module, and I get apparently I get this hints already. I can do this, and this is now getting the function compiled add function from my module, and I'm gonna call it with some numbers, and I get 5. Nice. So now we compiled Python to C code.
I think it's worth pointing out that although the binary and the Python file are called my module, so the name is the same, but it will give preference to the binary if it exists. The
Yes,
Python interpreter.
that is a good point. In this case, I still have the original .py module as well as the compiled version, but it will give priority to the compiled one. Okay, and now to make life a bit more convenient, let's move on to Jupyter Notebook, because we can actually use Python from Jupyter, which is actually very useful for debugging. But unfortunately, there is a bug in Jupyter, or at least in Jupyter Lab, that makes some parts of Python, the Python helper functions, not as useful as they should be. So I'm going to use the old classic interface to Jupyter Notebooks, because it should work here, and let's pray that it actually works. Even if it doesn't, then what you're losing is just some color highlighting. So it's not that big of a deal, but just to demonstrate that it's what it should look like, I'm going to use the old interface. So now I have here a new Jupyter Notebook. Python is implemented as an extension, so I need to load it. Load extension Python, and now it should be available. I can create the same function as before. That's why result x plus y and return the result. And now to tell Python that it should compile this function, we're going to use magic Python, and that should do it. And we can call the function. And the reason I started using this classic notebook instead of Jupyter Lab is because there's a useful magic called annotate or -a or just 2 dashes and annotate. And this will show you the generated C code by Python. And there's color highlighting that shows how much Python interaction there's in the code. And this is useful because with Python, we commonly want to minimize the amount of Python interaction because that's the slow part, and we want to get rid of that. Now here, everything is yellow, which means that there's Python interaction on every line. And the reason is that we have not really added any kind of Python extension features that could help Python remove this Python interaction part, which will be the next topic. But just we can here inspect the code. It's again not very readable, but at least it's only showing the relevant lines. This C code written using macros from Python header. It can be useful for some debugging purposes, but not necessarily. Like this is not very useful, for example.
Right. So yellow means that it's interacting with the Python interpreter a lot. How do
Yes.
we get rid of it now? Are there ways in Python to get rid of this?
Yes, and that is the topic next, which is adding static type information to Python. So as we discussed, there's a lot of boxing and unboxing of Python types going on because Python has to figure out, it has to check what type this variable is at any specific time. So if we can actually tell Python, or in this case, tell the Python compiler that, okay, this variable is going to be integer always, then it can optimize a lot. And this is also how C or Fortran or any compiled language with static typing gets there, kind of manages to be so fast. So with Python, we can actually add that. Python extends Python with a few keywords that we can add to code, which makes the code not valid Python anymore, but it will be valid Python. So usually what happens in Python projects is that we have files specifically with Python code, which we compile ahead of execution to machine code, and then call those from the main Python program. So in the case of just adding 2 integers, we can add this keyword int to a function to tell Python that these variables are going to be integers, like this. And let's look at the annotate. Okay, this is very good. So what happened? I told Python that, okay, these input variables are integers, and now it doesn't show any Python interaction on this line where it does the addition anymore. So that means there's no type unboxing or boxing going on here. There is still boxing going on the last line where it has to convert the result to a Python type. I can also do this. I can define the result variable as an integer with a keyword called cdef. But in this case, it doesn't really help much because it still has to convert the result to Python type. So that's a bit redundant here.
Yeah.
Good. So now if this was a real function that had to do some really heavy workloads, then this would be a lot faster than a standard Python function. But of course, just adding 2 numbers is fast also in Python, so it's not that big of a deal. One thing that which is the downside of static typing, of course, is that types really need to be integers. So what happens if I call this function with something that's not an integer? let's call it with floating point numbers, we see that it's still returning 4
Right.
instead of what it should be. It should be 4.8.
Mm.
And the reason is that when you're passing floating point numbers to your compiled function, the function is forced to reinterpret the inputs as integers. So it converts the floating point numbers to integers, which means dropping everything after the decimal point. So in the end, it's just saying, okay, I'm getting 1 and I'm getting 3 as an input, and it adds those up and it returns an integer.
Mm.
To make this work with floating point numbers, you would instead have to add something like float here. Remove that. And then rerun, and now it's actually giving you floating point addition. And if you've done any programming in a static typed language like C, then this is of course not news, but just something to keep in mind with Python, that the price to pay for performance in this case is that you really lose some of the dynamic nature of Python.
But at least it will prevent something very silly like passing a string to this add
Yes.
function, right? Yeah.
Yeah.
It will complain.
Let's actually try that. So we have a function that wants to take 2 floating point numbers. So what happens if I call it with a string? String. Yeah, it gives a runtime error.
Yeah.
Must be a real number, not a string. Meanwhile, if this was a Python function with no type hints, no typing, then it will pass the string to the function. It will try to perform this addition of an integer and a string, and it will fail at this point because integer plus string is not a valid operation in Python.
Right. Yeah. And even like adding 2 strings is a valid operation in Python, but even that will fail here if I.
Yes, that will fail because it's failing already in the stage where it's trying to pass the variable.
The variables.
Yeah, let's add some other string. So adding 2 strings is valid in Python, but it is not valid for this function because this function has no types fixed. It needs to have a floating point number as an input, as both inputs.
All right. Yeah. That's nice. And so we saw like how to compile with some small scalar inputs. How can we do the same with NumPy arrays?
Yeah, this was of course a very trivial example. A function like this is not something that you would want to Pythonize in real world usage because it's not the bottleneck. If it is, then your program is very interesting. But what you can, or what you may have to actually Pythonize is something involving NumPy arrays that does not vectorize. So NumPy is good for vectorized operations, but if the algorithm you want to do does not vectorize, then you're out of luck. You have to loop over the NumPy array and index it at different indices, and that's all very slow. So we can take this example here from the notes, and I'm just going to copy it in the interest of time and paste it to my Jupyter notebook. So what's going on is that we have a function called slow looper. It's slow because it is very slow. It's looping over a 2-dimensional NumPy array. We have a double loop here. And then it's assigning a number to every element of the array. So every array element gets a different number. So just to demonstrate this, and I can time it. I can measure how long it takes to calculate this. Slow looper. Let's use how much, 500 maybe. Yeah, it takes 40 milliseconds to do that loop when the array size is 500 times 500. Now let's do the same thing with Python. So Python has support for NumPy arrays, and to do that, I'm first going to copy the same function. I'm going to change the name to, let's say, Python looper, and then I need to do what's called the C import. So C import is a keyword added by Python, and this tells Python to import some something at compile time already. So in this case, we need to import the NumPy C headers. Otherwise, it won't know how to deal with NumPy arrays. And now I need to cheat and check what the syntax was. Yeah, okay, so it's just NumPy. So C import NumPy to get the NumPy C API as C NumPy, and we're going to import it as a different symbol. So this is Python NumPy, and this is NumPy C API. And so what we can do, first let's add some type hints. So the input is going to be integer. It's going to be the size of the array, or square of the size. And I'm going to add the magic to Python as this cell.
And we use CNP to declare the data array. Is that correct?
Yes, I should. So I'm creating the data array with the standard NumPy, which is still valid. Oops, sorry. But I need to declare the type. I need to tell Python that, okay, this is going to be a NumPy array of specific data type. And I need to cheat again and check the syntax because it's not quite trivial. Syntax looks like this. Use the cdef declaration keyword to declare a type. Type that we're going to declare is going to be cNumPy ND array. So ND array is the usual kind of actual array of NumPy. And then the type is specified here. In this case, I'm going to create an array of 32-bit integers. And the dimension also of the array, dimensionality is going to be 2. So I'm going to copy this and paste it here. And for some reason, tabs are broken. Okay.
We are in the wrong cell.
True.
Yeah.
So copy that here.
And now we called it int 32, yes. So maybe the array should also match numpy.int32, right?
Yeah, just to be on the same safe side, let's use the same data type here, because integer type, I think in Python is 64-bit by default.
Right.
So now that should have Pythonized, and then I'm going to call our new looper. It's called Python looper with the 500 times 500 array. And you can see that from the timing that the same loop was 10 times faster, which is pretty nice compared to the Python loop, like pure Python loop. Even though with so we did not test actually if we just Pythonize this pure function without any type hints. So that could help a bit, but the main issue is that indexing of a NumPy array is rather slow. So the indexing happens here, and this is a rather slow operation, which is why the usual rule of thumb with NumPy arrays is that you want to avoid manually looping over them and doing indexing like this. But with Python, you can actually do it because Python can optimize this indexing away.
Right.
And it can also optimize the overhead of interpreting a loop that Python does. So that gets optimized away when you Pythonize.
So we get rid of things like safety guards for going out of bounds from the numpy array, right? When you do
It
indexing.
it
inside
actually
array.
does not get rid of that automatically. So yes, that's
How do
a
we
good
do
point.
that? Hmm.
So what happens when you're indexing a numpy array? So you access a numpy array at some index. It will check, like it does some checks on the indices. It checks if the index is valid in the sense that it's not too large for the array, and it will also check the sign of the index, because NumPy wants to support syntax like this, like minus indexing, in order to wrap around the array. So it does checks like that. You can disable them with Python. So the decorators for those are here: bounce check and wrap around. And I can add them here. And now it failed because I forgot to do something. Oh
Import
yeah, I need to
Python.
import Python. So that now disables the index checking, which may or may not improve performance. If it does not improve performance, there's a write-up about that here, which has to do with branch prediction in CPUs. So this might not always be actually beneficial.
Hmm.
And if you do disable these checks, then be very careful, because then it's really not doing any checks and you can crash your program. So if I add a line here that tries to access data at, let's say, minus something something, that should crash, because it's not now checking the indices anymore. Oh well, it did not crash. Why?
Maybe if you go like more than n+1, something. Yeah.
Yeah,
Something
let's
like
try
that.
a very large index. Okay, I have
Yes.
crashed my Jupyter kernel. And with that, I think it's a good time to end. I have
Yeah.
successfully broken my program by disabling NumPy
Yeah.
safety checks, because I wanted to improve performance, but I was very careless, very reckless in doing that. So lesson learned: be very careful if you actually disable these checks
Right.
that Python allows you to do.
So
All
to sum
right.
things up, yeah, we don't Pythonize everything. We choose only the slowest parts, slowest functions.
Yeah.
Yeah, absolutely.
And also, like usually it's not like the Python works the best with elementary data types like integers, floating point numbers, and strings, but it's not that great for heterogeneous containers like Python dictionaries, because those can really contain any type. So it's just how to optimize those. And same for Python lists. Okay, sorry for going a bit over time.
Yeah, it is time for lunch break. So I don't want to stay very long and chat here. So I'm just trying to decide if we are going to meet back at 10 past, or, but I guess let's meet in time. So at well, at the hour, which is 1 o'clock Finnish time, Central European time should be about 12. And otherwise it's whenever it's the exact hour.
Right.
All right. Well, have a good break. If it's an appropriate time, have something to eat, and we'll see you in 50 minutes. Bye.
Yeah. Bye.
Bye.
Hello, hello, and welcome back. Hopefully, you had a little bit of time for eating some food and relaxing a bit. So, briefly before I introduce the speakers for the last part of the course, which again is after the scripting, is my second favorite part because it really goes to the core of reproducibility by making, for example, your own code reusable through packaging and by reusing other people's code with the version control and or dependency management. Just a reminder about the credit, since this is the last session, that you can read the required tasks at the link that is written there. And remember to send homework from your university email, because that's a requirement that we would like to, basically we want to give the credit to those who are students. And if you are a master student, you need to also verify that your study program actually accepts credit. But I don't want to steal any more important time from Simo and Ashwin. You actually already seen them before in the past days, so the stage is yours, and I guess we can go to Simo's screen share.
Okay.
Yes, so hello everyone, welcome back. So now that we have gone through a lot together already, like if you remember, we have gone from first creating the environment that you have been using throughout the course to learning about how to do scientific computing, and now becomes the interesting part of like, okay, you have learned how to do your own like scientific programs, hopefully, and now you want to share them with other people. So for that, we need to first talk about like how do we package that stuff, and then how do you like make it reproducible and stuff like that for installation. And we'll have 2 sessions on this, and this first session is about the packaging stuff. And so Ashwin, hello, what could you tell me about packaging? How should we package our projects?
Right. So packaging is an interesting topic. It's also important to think like when do we decide when a piece of code becomes a package, like when it deserves to be a package, right? So it could be very simple. It could be one file, and it can also mean that like you're writing a couple of functions within that file, and it's you start to reuse it in different places, different computers. Your friend starts to like it, they want it, they always email you. That's one reason maybe packaging is useful for you and your colleagues, your collaborators. So what packaging does is it puts all the Python code in, if you're talking packaging in Python, into a zip file or something similar to the zip file. It has some special extensions, and you upload it into a special server. The most popular server we will see soon. It's called PyPI, and that's how you create and publish a package in short.
Yeah, like these special files, they're often called wheels, Python wheels. So this is like Monty Python jokes all around. Like the Python is named after the Monty Python, and the wheels are for the cheese wheels from the cheese sketches. So like
Exactly.
there's weird naming conventions all around, but that's all fine. So
Right.
how do we like? Is there a preferred way? How should we organize our stuff when we have this sort of like we want to package our stuff together? How should we organize it?
Right. So the first thing you should do is you should have a couple of files which will become modules, because they will be made importable by the process of making it a package. So we need some files. That's the first thing that you need. And then and we also need some metadata to go along. For example, a license is important. That makes it legally possible for other people to download it and install it in their own systems. Without a license, it doesn't mean anything. It's supposed to be a private package, so people may not use it as you want. And then, of course, every package usually comes with a README describing what it does so that people can read about it before they install it. So these are the main components, and we will do a simple package in this episode, and we will try to go slow.
Yeah. So
and
let's get started. So
exactly.
I'll
Feel
have
free
a
to
new
follow.
folder here and let's get started on this. Maybe I'll
Yeah.
make it a bit bigger and
Exactly. So what
so
we're going to do is we open Jupyter Lab and we create an empty folder. And the first thing is to choose a name. Like choosing the name is sometimes most hardest problem for any project. So before we go to the step, maybe we could check pypi.org if this name actually exists, right?
yeah. So like in all cases, like if you have like a new company, you want to start a new company, like the first thing you do is you Google the name of the company and is it already taken, or like do you have the like the web page already present, like has somebody else already taken that? Because like if they have a big if they have taken all of the space, all the search engines point to them, or you just get confused with that project, that's not a good thing. There's also in these packaging indexes there can be a problem of like cyber squatting or this kind of like security attacks by like if you install like numpy or something with 2 M's or something like that. Like people have done these kind of attacks where they like publish vulnerable packages with small name differences. So usually you want to pick a name that is like not something generic. So of course, in this example, we'll pick like a calculator as a very non-generic name. But let's call it like I will call it like my own calculator, and maybe I'll put even the year after that. So let's call that our project.
Yeah.
Does that look fine, Ashwin?
Yeah. In a practical sense, I wouldn't put something like a year, but just to make sure that this thing is unique, we can assume that this is a fine name.
Yeah.
Right.
Like in an actual situation, you would of course want to put something that is like more
Descriptive.
More descriptive and unique
more
and that sort of stuff.
findable in when you search it in Google or something similar.
Yes.
So then you need what do we do now, Maximo? The files or?
Yeah, like we should probably have the files there, but if we want to use them in Python, we probably want to have them in a way that we can import them in Python, right?
Right. So then we need to give the package a name. So we call that package something very short and useful.
Yeah. So something we want when we do an import in Python, like we want to give a Python module name that is like something that we can import easily, like for example NumPy or something. And this can be different, but to the project name or what is in the PyPy index. But of course, like in best cases, it would be the same. So, but let's put a different one for now because we don't want to import this kind of a monstrosity.
Exactly. Yeah. And it's also done in the wild. For example, you might have heard of this package called scikit-learn. If you install, it's called scikit-learn. But when you're launching a Python and importing it, you will write sklearn. So it's a very short name. It could be the same name, but sometimes you can. Short is good, right?
Yeah.
Less typing. And then we put these functions in small files, which will become the module. The module is called adding.py, and the function here is called add. It does addition.
All of this is from the page. So
Yes.
like it's like if you want to do this later on, you don't have to like write it really fast. You can look at the page after the fact.
Yeah, and there'll be time in the exercise for you to catch up. So we create a subtracting.py with a subtract function. And finally, the third module, we call it integrating. And in that, we actually import another dependency from SciPy and reuse it to make our own integral function.
Yeah, actually, let's see.
So your package doesn't have to be standalone. It can rely on other packages to get help from. Now it's also a good practice to tie everything up so that you don't want to write calculator dot adding. So we create init.py, it's called, and this is supposed to be the top level of your package.
And this is like a chosen name in Python. Like it does this underscore is like internal like Python information. Like it has this specific format of underscore init underscore.
Right, exactly. And we will soon see when we install this package that this makes things easier to access
And
these functions.
we also here mentioned this kind of like a version string of what is the version of this module that we are creating. So this is again like this kind of like meta things for Python, and this is again like a chosen word.
Right, exactly. That's well-known practice. And then finally, like we said before, we need to give some description. So we'll write that as a readme.markdown file, readme.md.
Yeah, quite often, like of course, this thing would be like in a repository somewhere. Like you could probably use version control, and you would put this repository somewhere. But so we would have probably a pre-created the markdown already. But
Yeah.
let's now create it because we're missing it.
Exactly. Yeah. This is meant for humans, of course. And now our most of the main contents are ready, but we are missing a key piece, which is the packaging, like the machine readable part of it. So we will use at this stage a tool which comes in your Conda environment already. It's pre-installed. It's called Flit. And if you run Flit init, it goes into a flow where you can type in some names. Like here, we can give the name of the package, it's calculator CMO 2025, and the author name. We can give an email. You don't have to reveal your personal
Yeah,
email. Could be
I
something
would put
trivial.
something.
Yeah.
Let's promote alt.
And the home page, yeah, it could be your university name or the GitHub repository. That's usually done. And there are some good options that Flit does for you. Like you can choose which kind of licensing you have if you are familiar with those. Here we keep it simple.
Yeah. And you notice that the module name here it was different to what it demos like by default. Did it want to give the same name for the module as the file here?
Right.
But like we'll fix this afterwards, like because our project name that we put into PyPy is going to be a different one. So
Exactly.
what we get out of the Flit, we get this kind of a file, right?
Yeah. So it pre-fills all these questions and writes into a pyproject.toml file where all this metadata goes. So before we go into actually installing, we will show like even at this stage, you can import it provided you are in the right directory, right? So let's see how it's done.
Yeah, let's try it. So I'm here, like I have a terminal open here. Of course, I could use like a notebook as well, but let's use an interactive Python terminal for fun. And I will just start Python here. Let's try something fun. So there's an example code in the examples that runs some like complicated mathematics with this new package that we have,
Very
and
complicated.
then yes, and then we see that okay, it managed to import. So you notice that like we got this from calculator kind of a thing, and how Python recognized this is it looked like these init files, right? So
exactly.
it knew what to import, and there's like a whole thing of how do you do this kind of imports, and there's other things like you can have an all there as well, that you can do a wildcard imports and that sort of stuff. But let's leave that as an exercise for the home viewer.
Yeah. Right.
Okay, so how do we install this? Are we ready? Like, is this already ready for install, or do we miss something still?
I mean, we are using, assuming that this package requires SciPy, right? So we need to mention that somewhere. How do
Yeah.
we? Yeah.
Yeah, and the previous we also, well, let's first fix the SciPy thing. So let's for the project we can set dependencies, right?
Yeah. So the way to do that is to write in something which looks like a list of strings, and it can have more dependencies, comma separated as a list. And SciPy is what we choose. The other thing we need to tell, and the build tool that we are using, Flit, is what the module is called, the top level module, which is calculate. So this is different from the package name that we chose, which is right now calculator underscore Simmer 2025.
Yeah, so we are now using, there's multiple of these build systems that you can use. There's multiple of these initialization things you can use. We are just using Flit because it's easy and it asks those nice questions, so to create the PyProject TOML. But there's others as well, and you can give them their own options. So in this case, we are telling it that, hey, look for this folder for the Python files, not like this is the folder name. But there are other tools as well for this build system, but
Exactly.
for this case we'll use this one.
Yeah.
So are we now ready?
I think it looks ready.
Yeah.
So now we can, there is also a note we can mention that like it's possible to add dependencies from Git. Yeah.
Yes,
But that's
we
also
could.
possible, and there is a small comment on that in.
Yes, so we could add something like, for example, if we would want to use a repository from Git, we could do something like this. It like, or any kind of like pip packages or something we would want to use, like we could use it. But in this case, we don't need Xarray, so let's not.
No. Yeah.
Let's add additional dependencies that are not needed.
Exactly. And also, since we are mentioning this, for development, like for local installations, this is fine. But if you're going to upload this, PyPI will probably complain that you're using something which doesn't exist on PyPI. So be careful there. So with that, I think now we can describe the exercise, give an overview for what you are supposed to do.
Yes. So in the exercise, like you should do the same kind of like project, like what we were doing, like basically follow the instructions over here to create a similar kind of project. And now you can try to do a local pip installation of that project. And in the exercise, there's a hint over here that we are going to go to the package dependencies and environment management and stuff in the next section, but we haven't gone through there yet. So for now, there's a hint here on how you can create your own virtual environment that you can test out the installation. But yeah, test out creating this package first, and then creating a new folder, creating this virtual environment, and trying to install that package into that virtual environment, and see how it goes. And we should probably have around 15 minutes for this.
I would say so. Yeah. So 35 minutes past the clock, we will come back and discuss this exercise.
Yes. And ask any questions in the notes as well, like about the package management or package creation, if you have any.
Yeah, absolutely. See you.
See you.
Bye.
Hello, we are back, hopefully.
Welcome back.
So hopefully you managed to try out the thing. There's lots of lots of copy pasting needed. So it's sorry if there was too much in this time frame, but we can quickly demo what was the result or what you could have experienced. So first of like for this installation, like when we are trying it in a different place, we probably want to do it in a place that is not inside here. So we want to do the testing in somewhere that is completely different folder, right? So let's let's create a new folder over here, and then I'll open a new terminal over here. So yes, I have a new terminal over here, and now let's do the steps to get a new virtual environment for us. So I'll just copy this over here. Okay, so we now have a virtual environment, and let's do the pip install command. I will type the path as a relative path. So with tab, pressing tab, I can autocomplete. So I will install from the relative path over here, and it's the folder with the PyProject TOML, right? So
Yes.
that's what the pip install is looking for, the PyProject TOML.
Exactly. Yeah. And to note, while we're doing this, virtual environment is some sort of simplified version of a conda environment. It shields the Python from seeing other dependencies which are pre-installed.
Yes.
In your system.
Yeah, so we noticed that now it's installing NumPy, SciPy, and our calculator over here. So now we can we have it, so we can now try opening a Python interpreter and try the test code. I'll just copy paste this one over here. Yeah, notice that it works. So by magic, we have installed it over here. And when we did the installation, we used this editable flag. So Ashwin, can you quickly explain why the editable? That sounds like.
So what pip tries to do is not to copy over files when it's trying to install it. It creates something like a symlink. If you understand Linux language, symlink, it's like a shortcut pointing to the package folder, calculator, simu, in this case, right? So every time you make a change in your modules, then it's immediately reflected once you open a new Python interpreter. You'll have to close the Python interpreter to make these changes appear too. So let's try to make some change in the subtract function. Is that the
Yeah, let's add there like maybe a print statement or something.
Yeah. Let's say print subtracting, yeah, x and
y from x.
Yeah.
Yeah.
All right. And then now we skip the pip install because it's an editable install, right? And now if we run the same command that we did before.
Yeah, well, let's just run the. Well, actually, let's run the whole thing because it's easier to copy paste.
Yeah. And then we notice, like, while calling the subtract function, it managed to print something.
So this editable is really useful if you're doing like a development thing, right? Like if you want to test out things, and but of course, like in an actual, like if you want to use your code, you probably want to have it in a lockdown version state so that you can like be certain that what version you have installed and so forth. But if you want to do this kind of like development work and test out how it looks like the imports work and everything, you can do this.
Exactly. So for that, you skip the editable flag.
Yeah.
All right.
Okay. So should we now publish this package? And
Yeah.
probably we don't want to publish it. Like we don't want to like mess up. The first step of publishing is probably like testing it out. We don't want to like necessarily mess up the Python registry with more package names than needed, right?
Exactly. Yeah. So for that reason, we will avoid the pypi.org website. Instead, we go for the test pypi, which is like a test version of it. Just a note to all of you who are watching, we don't expect you to follow along at this point. We'll be going slightly faster, but good enough that you can follow. So first step is to log into PyPI, and what should we do? Is that what we do? Like we make sure.
Yeah. So if we want to log into
We have to-
PyPI, yeah, we have to get our account, and then we have to figure out this get this API key from PyPI. So do you want me to show it? Or?
Yeah, but maybe we build the package first, so we are clear on steps,
like
right?
yeah, like first off, yeah, we need to do an account for the place we want to push it. But then once we have those created, first we need to like build the package, yes, so that it's ready to be sent there. And so we want to put it into this wheel of cheese. So and for this we use this command, right?
Exactly. Yeah.
Yeah.
So this again should come pre-installed. If not, the way to install it is pip install build. And the way to work with this is to go to the package folder, where your PyProject.toml sits, and then to run this command python -m build. What it does is
what it does.
Yeah. What it does is try to create an isolated virtual environment for you on the fly. Make sure things like Flitcore, which is the tool that we choose, is installed, and then wraps everything under a tar.gc file and also a wheel file. So these are two different special formats. And you'll find them in the dist directory, dist for distribution. So we are supposed to distribute this somewhere. And that somewhere is going to be our testpypi.org.
Yeah, and for this, like, just again, like a reminder, like if you want to try this out, you can create an account in testpypi and then push it there. But yeah, don't go messing about, like, don't go messing the PyPI registry for like if you don't need it. Like, of course, for your actual projects, publishing them in PyPI, that's the place to do it. But for this kind of like messing around, we don't want to like cause problem for them. So the test PyPI is meant for that, where you can put like arbitrary crap in there and try it out like your projects. So for that we use a different tool, right?
Yeah. So here we are using Twine. It used to be the tool, and we are gonna do that. So Twine has a subcommand called upload, and when you write that, you give the list of files that you want to upload. Here it's dist/star, with meaning these two files that we created. And then it asks for something called an API token. It doesn't ask for the password. So this is something you need to create from the website. Can you show how to get that?
Yeah, sure. Let me just I have it somewhere open here. Yes. So if you log into
are you
yeah,
sure?
just a second.
Yeah.
Yeah. So yes, so if you go to test PyPI and log in there, you can then in your account settings. Okay, it wants me to put my password in. Not now. Yes. So once you have the account, you can then in your account settings ask for this API key. I won't be showing it because like I don't want to dox my emails and stuff like. But it's underneath there, like yeah, you can create an API token over here.
Exactly.
Yes. So
yes. While creating a package for the first time, it makes sense to give the API token access to all your projects. But if you're running something specific, maybe it makes sense to create a token later on after you upload your first release to a token specific for this package. And this makes sense in things when you're doing this packaging in an automated way in GitHub and so on, which we won't show, unfortunately.
But so I will now. Well, there goes my token. Well, I've
That's
had
okay.
to delete it, but this happens. Like this is a good example of like
what not to do.
Yeah, like when how do you revoke an API token? Like you post it into the internet and then you revoke it. So, but okay, this already exists because I already did an upload. Let's do a quick change over here. So let's me in my calculator, I will change the version. I will upload the new version,
and then
and have to do the build again.
Yeah, clean the dist first, though.
Oh yeah, that's true. Yeah, so I cleared the dist, and now I will build it again.
So this is how you create a new version.
Yes,
so that's
I
a bonus.
Yeah, bonus lesson. Yeah, and then I will upload it and maybe publish my API key again. But this is why you use the test pipe API, so it doesn't matter that much if your API key is valid.
Yeah.
So, so now it gave a response that it was successfully published, and I can maybe show it over here. Let's see. In the test pipe button packaging index, it's now there, and it probably has it has the README over there, and it has a release history. So I have two versions over here.
Two versions, absolutely. Yeah.
So should we now quickly try how to install it from there and then
exactly. Yeah.
So
for that we create a virtual environment, another one, fresh one. So
yes, let's go to. I'll create a new folder over here. So let's py test. And I'll open a new terminal in this folder. Yeah. So then let's create a new virtual environment. Yes, over here.
Right. So in this snippet of code, what we are trying to do is create a virtual environment. Try to
copy these parts.
Yeah.
Go right ahead. Yeah.
So create a virtual environment, activate it. So the pip from now on will be the one inside the virtual environment. And then we tell pip to actually look for this package in test by API. That's what the flags are.
I needed to cancel the previous installation because I need to give it the name of my package. So,
yes. All right. So now things are more clear. And the extra index URL is to fetch SciPy from.
Yes.
So unless SciPy is already in test by API, which maybe it is.
Yeah. So I think this is a good place to wrap it up. We need to have a break before the next session. But before going there, maybe we can mention that like there is good extra information in the page, like if you want to look later, about how to do a Conda package, and also about the whole ecosystem, right? If you need to do something like C compiling for your Python package.
Exactly. So Flit is the most simplest of the build tools of all 5 that we have listed here. And here is a small decision tree where you can choose depending on what you need. If you're doing something more complicated, you might need something equally capable when you're releasing to PyPI. if it's you're releasing into Conda, then we have listed some instructions for that too. But typically, people don't upload a package to Conda themselves. They rely on something which is called Conda Forge. It's an automated GitHub-based organization where you upload small recipes, as it's called. We also show how to build your own Conda recipe in this episode. So you can take a look later on after this episode.
Yeah.
Yeah.
And with that, I think it's good to have a break. So thank you,
Absolutely.
Ashwin, and we'll return at the hour about and talk about dependencies and virtual environments and that sort of stuff. So
Yes.
yeah, 10-minute break. So see you in at the hour.
And keep your questions coming. See you then. Bye.
See you then. Bye. Hello, and we're back.
Hi.
Hopefully you had a nice break. So we have a new instructor here as well, Sabri. Do you want to introduce yourself?
Yes. Hello, everybody, and hope you're having a nice time today and learning so many things. So my name is Sabri, and I'm joining from Oslo, Norway. I mean, I do Python programming, but I'm more in the system level support. So I'm hoping to learn some things, how Simo behaves when he install packages, and and maybe we'll see some opportunities to learn more things from each other.
Mm. Yeah, that sounds nice. So okay, let's like at the start of the course, we started, of course, with creating our environments that we have been using throughout the whole course. So it might feel a bit strange that at the last lecture we are going to be talking about how do you manage these dependencies, but yeah, this will become more important for you when you want to have your next project. You want to start your own project. You suddenly have to like work with these dependencies. So we had done the work for creating that environment and putting the instructions on how to do it, but now we are going to be telling you how you can do that as well for your project. So what is a dependency? It's, well, in general, it's like some package, like a Python package or a thing that your code needs. But like we have been talking throughout the course that like many of the scientific Python packages, they are not only Python. They're not only Python. They're underneath it is a layer of like lower level code like C code or Fortran or something else that makes the thing fast. And nowadays with like deep learning and stuff, like often people have to do GPU stuff as well. Like they need to use GPUs or graphical processing units to speed up their codes. And for these, you need additional like libraries that that make those codes work. And there's also like people are using Python to do like user interfaces, like they're using it to create their editors and whatever. So you might need all sorts of like graphical libraries as well. So there's huge bunch of stuff that can be in these packages. And how they are usually like how is this handled usually?
So, Simon,
yeah.
the in the lesson before, you
Yes.
and Ashen, you mentioned several times about packages, and you also made a package. So
Yes.
now we are talking about additional things we need to run our packages. Is that correct?
Yes. So like if we have something, we create our own package, and we have something that it depends on. Like for example, in the previous lesson, we had a package that depended on SciPy. So if we have our own piece of code and it needs imports from a Python module or Python package, these are what we want to install. And what for efficiency's sake, these are like usually pre-compiled or pre-created somewhere. Like we download them somewhere. Like somebody like a like some nice person has already created us usually these packages and provides them in the internet, so we can download them without having to compile the code ourselves or do all of the necessary thing that we just did, like the building of a package and that sort of stuff.
So without writing NumPy ourselves, we can use NumPy and develop from that place.
Yes. Yes.
Yeah.
Exactly. And for these, there's basically like a big ecosystem around Python, and this is like why Python is so popular for scientific computing, because it's so easy to extend it. Or in general, why Python is so popular. It's easy to extend it with other pieces of code. Well, relatively easy at least, but easier than, let's say, extending Fortran or something. So there's like big ecosystem of these packages available, and there's basically two major providers, at least in the open source world. There's probably others as well, but two major like ways that scientific codes are often provided. So we have already been talking about PyPy. So this is Python packaging index. So this is basically the go-to place for Python codes. So there's a huge number of different packages there, and you usually use pip to install stuff from there. Nowadays, there's been a new tool rocking the boat called UV, which is really fast, like this PyPy installer. But there's others as well, like Poetry, and there's a lot of different things, tools that can install from the Python packaging index. But pip is the most common one. UV is this kind of like a new player that is getting very popular. But basically, PyPy provides a lot of Python packages. And the thing with PyPy is that if you have code there, if you have pure Python code, that rolls very nicely there. But if you have something that has external library needs, so for example, if you download NumPy from PyPy, what you also get is OpenPlus libraries. So these are like linear algebra libraries that are embedded into the wheel. Like it's inside the wheel, there's these libraries that make NumPy work. So if you need something that has like external requirements, that needs to be put into the package. And that's why often in PyPy you find things like, well, pure Python code packages, but other packages, but those have been like embedded with the requirements needed for those, like those library requirements.
Yeah, but we are talking about some limitations, right? Later on, we'll talk about Conda, where you can integrate more system level packages. But now maybe you're talking about, because NumPy might use C underneath, it might need some dependencies and then some linked libraries.
Yes.
And you mentioned the word wheel. So wheel is it like a pre-compiled, like a tar file, or
Yes.
like a collection of things, but it comes for your operating system, isn't it? So is there a better way to explain a wheel?
No, yeah, that's exactly right. It's basically like a compressed file that has all of the stuff in it needed for it to work. Of course, like packages can have dependencies to other packages and so forth. Like for your code that uses NumPy, it doesn't need to package NumPy inside of it. It can depend on NumPy, and NumPy then can package whatever it wants inside of it. But basically, PyPy is this sort of like big ecosystem. It has huge number of packages, like I don't know, probably millions at this point. But it's a huge ecosystem. And the other big ecosystem.
Keep your questions coming up. So we'll talk a little later about dependency and conflict. So the good questions, right? Keep them coming up. We'll talk them little later. Take them a little later. Yes. Go on, Simon.
Yes. Yeah. Do ask questions. The other big ecosystem is Conda, which is like that was already mentioned by Sabri. And this is basically like Conda is this kind of like, it goes one level deeper. So what it does is that basically people were noticing that there's a lot of these lower level libraries that are common to many other packages. And what if people want to have different versions of these lower level libraries or different things like that, or they want to use the same, like they don't want to put the same like plus library for every package. So what if they would just use the same one? And this basically, like there was this company Anaconda Incorporated that created these tools, but nowadays there's a big open source ecosystem providing these packages. And Conda is basically like almost like an operating system kind of like package manager thing. Where it can provide like all sorts of like tools. There's all sorts of like graphics tools and weird stuff and lower level like compilers and build systems and all sorts of like tools provided in the Conda ecosystem. And we're talking about like again like tens of thousands of packages of different tools. So if your case is like you need a much more like base level of like installation, you need to have like some libraries for your code. Let's say you need to compile something, or if you need to make certain that everything plays nicely, and there's lots of these like complicated library things, then Conda is your friend. So Conda basically like takes it one level, like ups the ante a bit. So PyPy provides mainly like Python packages that then you can import, and the dependencies for those. Conda provides like basically an operating system, like lots of packages inside of there.
Yeah, so this OS level dependent is so people who do use a lot of machine learning stuff these days, right? So if you think about Python, if you want to install this PyTorch library, for example, it will come with PyTorch and the Python APIs and the maybe C code, but it will not come with CUDA. But if you CUDA or ROCm or whatever that additional things you need to interact with the operating system level access. But the Conda, it would also pull in the OpenSSL libraries and CUDA and other stuff.
Yes, and there has been there's this kind of like push and pull between these two ecosystems. Like they are not incompatible with each other, but it used to be that installing CUDA was like PyPy couldn't install CUDA, so Conda was very popular with stuff that used GPUs. But nowadays, like NVIDIA has started to actually publish CUDA in PyPy, so people have switched back towards PyPy. But they are not like there are different ecosystems, but there's interplay for all of these, and one is not better than the other, but it might, like, certain environments or certain tools that you want to use might be more supported in one ecosystem than the other. So it depends really on the use case that you're doing, and where, like, which is the better solution for you. I'll quickly
Regarding
explain.
this, so sorry. Could you explain about this Anaconda and Miniconda, and there are so many versions before we go further.
Yes. So I was going to explain like the Conda ecosystem, because like this is something that that sometimes can get quite confusing, because whereas in PyPy it's basically like you have a pip and then you have a PyPy, and then it's like that's the thing that you usually need to remember. Like you have the PyPy, which is the stuff where the stuff comes from, the index, and then you have the pip, that is the installation tool. But in Conda you have this kind of like this bunch of different things, because it was originally created by this Anaconda Incorporated. So they have their own like repository, their own like proprietary channels, and they provide this mini Conda installation and this Anaconda distribution. And these are not free by default. Like there's licensing, like you can look below, there's like links to the terms and conditions and whatever, and it's free for certain academic users, but not for every. So if you're going to be using these, do check that if your licenses apply. But in most cases, we recommend that use the open source alternatives. So there's a wide community around this CondaForge channel. So this CondaForge provides like tens of thousands of packages, and it's maintained by an open source community, and it contains like open source packages. So they are free, and they provide this mini Forge installer that you can use to create your environments and your Conda environment. So if you're going to be using Conda, do be mindful of what you're using to install the stuff, and whether you are allowed to use the free version or not. So check the licensing, but the Conda, in the Conda community, there's this free side, and it's very well maintained. So so we have been talking about what are these like ecosystem. There's the PyPy, and then there's the Conda. But how do you actually like do something with these? Like how do you actually like then manage your project? How do you get stuff into it? And the real question is, there was a question previously on the previous session, like why are we creating virtual environments? And the reason is that, well, in best, like if you want others to use your tools or your code, it's best to provide them with something that they can like installation instructions that make it possible for them to use those. And for that, Python uses these virtual environments. So virtual environments are basically like you do a self-contained installation of Python and all of the packages you want to have, and you put them in a nice area where they play nicely with each other, and they don't like mess up stuff outside. So it's like basically if you go to a zoo, if you take all of the cages out, like suddenly all of the animals are running around and it's going to be a horrible mess. But if you put like the cages, like if you like zoos or don't like zoos, that's a different question. But if you have the cages there, like then the lions won't eat the gazelles. And this happens with Python environments, kind of like if you have one code that wants certain things and another code that wants another thing, like then it's not usually possible to satisfy both of these requests. So you want to have these kind of like gardens, like walled gardens for each of these, and like Python codes. So these separated environments. So you put
So
your
yeah,
lions
so
in one place and you put the gazelles into another one.
another one, and then that's a good analogy, because there was a question about like conflicting dependencies. So the Python doesn't just fail because of conflicting dependencies if you use the environments. For example, as you said, gazelles and lions, they should not be in the same cage. You could have two cages. So that's a good
Yes.
way to explain that scenario. So you could keep the compatible stuff together, and when you need an incompatible thing, not try not to force it inside that, but create a new environment.
And there's, for these virtual environments, there's multiple ways of doing them. You can use like the Python by default, it has this venv module, which you can use to create virtual environments. Then the UV that we also mentioned, that can do those. Conda and Mamba can create these environments. And then there's this package called virtualenv in pip that can do those. And there's plenty more. Like there's a list of non-exhaustive list at the bottom of the article or the lesson if you want to look at those. But there's lots of different tools that you can use to create virtual environments. But the main thing to capture is that if you have a virtual environment, you don't mess up other stuff. Like if you have it there, it doesn't like spill out to other places. It doesn't mess up the lions won't eat the gazelles if they are in the same like enclosure. And you can have the specific things that those animals or packages need in that enclosure and environment. And if somebody else wants to create the same kind of environment, you can just tell them, hey, this is what I did, like this is the things needed, and they can create it as well. So it's very important if you want to share your code and you want other people to use your code as well.
So there's a question about if when you have a Conda environment and if you do a pip install, it'll install in that environment. But if you do a apt-get install, it's like a system level installation, like on Ubuntu system, it'll install on the system level. So you said that it's like operating system, but that was just like a reference. So it doesn't, the Conda does not create a operating system itself, but it's even less than a container. But if you install something system level, and if you install the same thing on the Conda, then the Conda will override. So don't try to, like, if you get into this rabbit hole where you have to fix something, you try so many things. If you have a system level library and a Conda library, and then when you activate the Conda became the prominent environment.
Yeah. So basically, what we want to when we have some code, we want to step into a realm where that code works, and that's basically, we don't want to like think about, okay, what's in the wider world. Like we don't want to think about the global Python installations or anything like that. We want to just have the stuff that we need. And that's what the environments basically do. Like we just put the stuff we need, and then we switch to that realm or that place where we have the packages that our code needs, and just those packages. And like it used to be, like back in the day, like 10 years ago or something, that whenever people were doing their installations, they were using like installing system level things, and suddenly their operating system was crashing because like the operating system also depends on Python. And if you change the Python version or whatever, suddenly you break your computer. And suddenly people realize that, hey, actually it might be really nice if we could do these separately, so we wouldn't like always have to reinstall our computers when we do a wrong installation. So that's why virtual environments exist, and this is same for all sorts of programming languages. This is not a Python specific thing. Like this is every language nowadays has its own idea of virtual environments. But
So
okay,
your Zoom example, Zoo example, for example, somebody asking whether it's only for Conda, but it's also relevant for Python environment that you're going to show. So both Python and Conda environments, it's relevant, the example.
Yes.
Yeah, go ahead. Yeah.
Yeah, so lots of talk. We have done lots of talking, less coding. So let's actually like look at something that can something that resembles like an actual example. So how do you create these these environments? So let's first look at Conda. So in Conda, we highly recommend that you create these environment.yamls. So this basically is a specification of what your thing needs, what your environment needs. And in this case, it's like you give it a name, you tell where do you want the packages to come from. So these are these so-called channels of where the packages come from. And then you specify what sort of dependencies you want there. And once you have this, you can create your environment. So let me try this out.
So you want do you want our learners to follow, or because
we have an exercise?
Right?
We have an exercise coming where learners can do the same thing. So I will create a new file, environment.yaml here, and I will copy this stuff here, and then I will do conda env create, and then the file name with the -f, and then the environment.yaml. Well, that won't work because there's no conda in this environment. Well, that's fun. Do we have Mamba? No. Okay. Let's not do the conda example then. Let's do the virtual environment one. So we can jump straight to the next one. So if you want to do a virtual environment with pip, you can write stuff into this requirements.txt. So this is another standard, and it's like just the packages that you need, and you write that. You create a new file called requirements.txt.
So now this is a text file, and the earlier one is a YAML file. So you saw some structured. So if you have created here, you can just write text, but in the YAML you need to maintain that structure, mentioning the channel, for example.
Yes. And in the case of virtual environments, I will have to first create, like Conda will create the environment like for me. But in the case of virtual environment, I first have to create the environment. And then whenever there's these environments, we need to activate them. So I have now here the virtual environment.
Could you explain this the command a little bit? You type Python and the -m for some module, and then
yes. So in this case, we are using the module of venv, and then we tell it to create virtual environment. So in Python, there's this it provides this module called venv, and when we call it like this, it will create as a virtual environment. And what it has over here inside of it, it's basically like a mini operating system installation that only has like Python installed inside of it. And when we run this source activate from that, so we run this we run this script. What happens is that we activate this environment, so we get into that environment. We go into that environment. So now it's active. So basically, our Python version has changed, and where the packages come from has changed. So you can see that the version has changed. So now I'm in that environment, and I'm in the world. I'm in the lion's cage now, like over here. So and over here I can do the installations I want. So I can run the pip install -r and the requirements.txt. to install the packages mentioned in the requirements.txt.
Yeah. So until that installs, Simo, so now you use the requirement file, but you didn't do like a pip install numpy, but instead you collected them in a file and you're installing it. So what are the advantage of doing that?
Yeah, and this is a really great question, a really great point. So why are we talking about these files? Like, why can't we just install stuff here? And the reason is that, like, if somebody wants to recreate this environment, like, you need to have instructions on that. And if you want to recreate it, like, you do something and you don't, like, later on remember what you did, like, if you haven't logged it anywhere, you don't remember it, and you don't get the same result. So that's why we always recommend that you use these environment YAMLs and requirement TXTs to lock down what versions you're using. And it's not only for you, but it's also for the tools as well. So what these tools do, like Conda, what UV, what PIP, all of these different tools do, they have a solver inside of it, and they try to like figure out what packages you get. Because like I mentioned, these packaging indexes have like not only they have like millions of packages, but for each of those packages, there can be like hundreds of different versions. So if your code needs certain versions, we'll talk about version numbering and stuff a bit later. But if you have certain versions for the code, you need to let the solver decide what versions to install. And if you give it partially information, like if it give it the information that, hey, like here's a package I want you to install, and then later on you say that, hey, install this package now, like it doesn't know about the previous packages, so it will try to do what you asked it to do. Like if you first say that, hey, like paint this wall green, and then next you say that, hey, actually I want this wall to be red and these other walls to be red as well, then it suddenly everything is red. And so it's well, that's a bad analogy, but basically, like if you install one package and you install then another package that has a stricter requirement, suddenly it can like remove the previous package and it can overwrite stuff.
Here the Simo, the NumPy, Matplot, and Pandas, the solver would check all these three packages, so it will install compatible three packages. But if you start with NumPy, it will not check that compatibility. And when you're installing Matplotlib, if the earlier NumPy is not compatible, then it takes time. And also, there might be conflicts. And the UV tool that you mentioned earlier, it has a faster solver, isn't it, than regular pip?
Yes, the UV has been written with Rust, which is again like a testament to how extensible Python is. That like the solver is written in Rust, and it's much faster and more compatible than pip solver. So that's why it's quite popular, and so it can do the installation faster. But yeah, basically, once we have done, like we see now the installation happening here, and we can see like what's being downloaded, what's being installed, and now we have our environment, and we can use something like pip list to list what packages we have in that environment. So we have now this environment, and let's say I want to recreate this environment, I can use the same requirements txt to do it again. So it's very easy to keep track of what your program needs while you're doing this. And I think with this, it would be good to have you try it out and create a quick environment yourself. So we can have like a small example or small test. So for example, try with the venv. That should definitely work if you're missing the Conda like I did. But if you have the Conda, you can try the Conda version as well. But try creating this virtual environment, and we'll be back in 5 minutes, so 35. And then we will talk about all of the complexities that go into these environments, like versioning and stuff like that.
Okay, so is that we break for 5 minutes for everybody to try it out, right?
Yes. Try out creating, let's say, this virtual environment here.
Okay.
Hello. Yeah, this was a short exercise break. We don't have that much time, and there's so much discussion happening in the chat, so it's good to address all of the questions, because like this is a major question for Python situations often. So first off, I want to clarify a few things about the like terminology in Conda ecosystem. So first off, there is this concept of a channel in Conda, like, and channel is basically the place where we get the stuff, and there's multiple of these. Like different projects have their own channels as well that provide like extra packages and stuff. But Conda Forge is the main channel for open source places, and then there's this kind of like Anaconda channels. They are listed in the document over here. So there's these package repositories and these software channels mentioned here. So you can check on these, but we highly recommend you use the Conda Forge because it has most of the stuff you need, and it's the open source alternative. And then there's these lots of like these different ways of getting these tools to you. And then they often contain like either the Conda or the Mamba installers that you can use to create the environments. There was also a question about like, can we have multiple like environments loaded at the same time? And this is not a good idea. like the idea behind an environment is basically like you have Python there, you have whatever that your program needs and that stuff. And once you start to get to this kind of like, if you try to like merge stuff from different places, it breaks the idea of an environment, right? Like you want everything you need in that one environment. If you have stuff coming from outside, it's basically like you have a cage and the cage door is open. So is it really a cage anymore? Like it doesn't anymore like have the same effect that it's supposed to have.
I mean,
And that's why
connecting
we
the
want to
gazelle's
have
cage and the lion's cage with a tunnel.
yeah, basically, and it's
Right?
like suddenly it doesn't serve the purpose anymore that much.
But workflows, Simon, like some workflows in like React scenarios, you might need different versions of package workflows.
Yes.
So you could activate and deactivate environment. So maybe next time when you're in the terminal, you could also show how to deactivate it. So you could activate another terminal if you have time later.
Yeah, like you can like, for example, I usually have like, I don't know, like maybe 20 different environments going for all of the different projects and tools I want to use. Like it's so much easier to have a separate environment than like trying to figure out one big environment that serves all of the things I want to do. And around this topic, like we could talk quickly about how you are going to what is the best practice of working with environments. So how do you like add, for example, packages? Like you create an environment, you notice that like I actually need to import these packages as well. Like how do you add it to the environment? So you can, like if you want to like create problems in the long run for yourself, you can just try to install it into the environment, and then you forgot that you installed it into the environment, and now your environment YAML or requirements.txt no longer represents what's in the environment. So this is not usually a good idea, and it also creates the solver problems that we mentioned. So the better solution is to try to add it to the environment YAML or the requirements.txt, and then update your environment. Try to do the installation again. And often, if you're like suddenly you have if you have a package that has a very different needs than the other already existing packages, it can create all sorts of like deadlocks in the solver side, or you can see that, okay, like something is being removed and something is being installed and something like weird is happening here. And then you notice that, okay, like maybe like at this point you should like notice, or you should like be careful and notice that, okay, like this new addition to this thing suddenly upended the whole thing completely. So maybe it's a better idea to just recreate the environment. And that's usually the best approach. Just like take the new requirements.txt that you have and just create a new environment out of it. Because it usually doesn't take as long to create a new environment than try to fix an environment that is like getting broken. So it's better to just like start afresh, because
So
it doesn't take
good,
that long to install.
That's very good advice, Simo. Thank you. And in addition to this, what the command we see is that we expect the environment.yaml file to have the same environmental name inside for this update, and also the same channels.
Yes.
So let's say if you have a different channel, it might bring out different versions, because depending on the channel, the default version might change, and it might actually create more conflicts and rabbit holes than what you, if you follow your advice as, create a new one if you need it, that might, save a lot of time.
Yes. So it's like when the lions are already in the cage, it's a bad idea to start renovating the cage. like it's basically stuff can get wrong and the lions can escape, and stuff can like trying to fit out different like things there. Like it doesn't necessarily go well. So it's better idea to like create a new cage and then move the lions there and then like live with that situation. But okay, so we talked about like this version, like this environments, but often the best idea is to give very wide version ranges, because that means that like when you create an environment, you of course create the environment in that time. Like when you create the environment, it suddenly like it doesn't update automatically, like it doesn't like magically keep up to date of what the ecosystem is moving forward. So it's like now something that is like actual realization of that environment YAML or requirements txt. But as time moves onwards, like the packages upstream will change. And that's usually a good thing, because you want new features and you want your things to be up to date with those things upstream. Like you want your thing to be installed with the current versions that are there. But
Can
sometimes
you show some details of what you mentioned about these versions in the slide? Can you show some?
Yes. So sometimes you want to lock down versions. Like you want like maybe your code needs certain versions. There was a question in the chat about Python 2. That's like a really old thing already, but some code still use Python 2. So it's for those it can be like quite difficult to get the versions installed. In some cases, you might need to use other tools like containers and stuff like that to make certain that you have like these really old environments installed. But in many cases, like you might have a situation where you want certain versions. Maybe a code is written with a certain package, and now the package has updated their whole style. So, for example, NumPy updated recently from version, well, not that recently, but few years ago, they updated to version 2. And some codes, of course, broke because of that. So some codes only run on Python NumPy 1. So then you might want to specify something like this in your package if you don't have time to update your code to work with version 2. So of course the better, like if you want your code, like Rolling Stone gathers no moss, right? Like if you have your code and you want it to be usable in the future, the best option is to update it when the future comes. Like when the package is updated, is to update your code. But sometimes you don't have the time, or you want it to be like, well, want it to be working, but you don't care about the longevity of the project. So then it might be a better idea to lock it down to certain versions.
So here, Simo, you have this, for example, the matplotlib, it has 3 numbers, like 382. So the major version and 2 as a patch version. So do you have to be this specific? And which of these numbers, changing these numbers could break your code?
Yeah, so usually like these numbers are called, there's this semantic versioning that is usually followed by most people or most projects, where the first number is kind of a major number that is like major changes to the APIs and stuff like that. The second version is a minor number, so that's often like new additions, but nothing will be deprecated. Often, sometimes there can be deprecated functions as well. And the last one is like a patch number that is like if it doesn't matter at all, then the like patch number is increased. But different projects have a different versioning scheme often. But in most cases, you don't have to like put your like version to be this specific like patch version or something like that, you can put stuff like this as well, like that is compatible with a certain version. Then it can like give you like versions that are higher than like 2.1, but still compatible with 2.1. So this is a good idea, because then it gives the solver leeway on how to solve the environment. Like if there's another package that requires a newer version, and you have you want like you force it to be too strict, then you can like make the solver's life hard for it, and you might get like really old version of a software suddenly. So it's usually a good idea like put requirements or these kind of version locks when you need them and when you want these when you want certain things to be stable or working, but only for those ones that can cause problems. And usually like the version locks start appearing the later, like the longer the time was when the requirements.txt was created to the time when, well, you're now installing it. Like the longer the time, the more likely is that you have to version lock something.
So here, Simo, we have mentioned the Python version as well. So because we are creating the environmental file according to your advice in the beginning, we might not know all the versions. But in this file, if you mention 3.1 as 3.11 as Python and NumPy as this version, would it automatically, if we don't mention the version of matplotlib, would the solver figure out the matplotlib version, or it would try to install the latest version and just break everything before that?
Yeah, so it would try to find like basically like what these do under the hood. There's like SAT solvers there, so they basically like at least UV and Mamba and Conda use those. I think Pip uses similar kind of thing as well. But basically they create this kind of like a huge list of like rules that needs to be followed, and then they try to figure out a solution, like a proof for that that huge list of rules. So if you have this version, matplotlib needs to be higher than this, and there are some versions of matplotlib that require numbers that are like numpy 2. They require numpy 2. Then those are like out of the question, because like this other rule suddenly forces it. So it basically tries to find you the like the solution for this kind of like multi-dimensional problem of like these different conditions that need to be satisfied. And if you give it more leeway, like if some packaged version doesn't matter, it gives the solver more leeway of finding possible solutions.
Yeah.
And
so Simo, there's a like when you do these things, so the packages get installed, and we didn't mention anything about where do they get like placed, but there's a question about how do we sort of place a package in a specific place. For example, on HPC systems, for example, we don't want to do that on our home directory. Sometimes it's limited when you work on a shared computer.
Yes, I will address that just in a minute. I will quickly mention that if you are working with like if you want to get the version numbers for existing environments that you have, you can, or what's in your existing environment, you can use this these export functionalities to get those. We don't have time to go through them, unfortunately, but you can check them over there. And if you want to like the best case or best place to put these kind of like requirements, if you have like a paper or something, like you usually want to have a requirements.txt that is applicable for that paper. So these were the versions that were used. So in those cases, it makes a lot of sense to lock down all of the versions. But often, if you have the code still being developed after the publication has been done, you want to have it in a separate like requirements.txt file. So these are the exact versions that you can use to replicate the paper. But then if you still want to continue developing, then you have another requirements.txt or environment that doesn't have these lockdown versions. But I will quickly address the excellent point that Sabri raised from the.
So it was a question actually from one of our very curious followers. So thank you for that question. I'm just going to transfer that thanks to that person who asked it.
Yeah. So that is exactly like a good question, and like you can, with virtual environments, you can create them all over the place, like where you want to like put them. With Conda and with UV, they do things a bit differently. So UV wants to like put stuff into the current folder where you're working on, and then Conda has this like central repository of a central place where it puts all of the environments. So everything is in that environment place. But what all of these tools do is that they download a lot of files. Like that's the thing. Like whenever you do installation, you can get like gigabytes of files depending on what sort of libraries you're using. And the important thing is that where those files end up. And most of those end up into your home folder by default. Like all of these tools, they use home folder by default to cache all of the downloaded files. And then they unpack them to different places. And Conda and UV try to reuse the packages as much as possible. So they create this kind of like package cache where all of the packages have been unpacked. And then every new environment that you're going to create, it's going to like link, create a shortcut to those packages, so that like as little as possible, as little space is used as possible. And usually you want this cache to be in the same file system as where your environment is, so that like it doesn't have to go across the file system boundary to another file system. Might be too technical here, but what you want to do is like place the caches into the same file system. So if you're running stuff on the HPC system or something, you want the caches to be in the same file system where your environment is going to be eventually. Pip doesn't do this, so Pip just copies the files there, so it uses a lot of extra space. So yeah, you can put those environments wherever you want to place them, but they will use a lot of space, so you can quickly run into like quota issues. And there's also the question that like many of these tools, like if you use Python, like virtual environments or Conda or UV or whatever, they will create a huge number of files usually. So in an HPC system, you might want to check your like system administrators guides on how to like maybe containerize these environments. So to put them into yet more strict enclosures, so that you use less files to do that. Unfortunately, we don't have time to go through containers
but the
here.
environmental file you created, you could also use it to construct containers. Like if people know what a Docker file is, for example, container files, you could use this same files to create it.
Yes.
And I think we finished, like, I mean, we went through most of the basic concepts, and I think it's a good point to discuss a little bit about before we end some problems as well. So when you install packages, if there's an error, try to read the error a little bit. Sometimes you misspell it. And the packages that you downloaded, they downloaded the wheel file. That means it will not be compiled on your system. But some packages, they might be compiled, especially if you're on a Unix system, and reading the error a little bit closer, or using some large language model to sort of help interpret the error messages would help, rather than just trying the same thing over and again, and then going through rabbit holes and messing up things. Start with the environment, create a requirement file, as you said, and if it fails, try to read the error messages a little bit more, and then you could even delete those folders. Like that's the like the advantage of having environments.
Yes. Like the advantage of having environments is that like if something doesn't work, you can try to recreate it from scratch, and like it's the same as like like restarting a computer. Like it suddenly works better when you restart it, and like you don't know what it solved, but something was solved around the way. And it's similar to the environments, that if something doesn't seem to work, like if the environment doesn't seem to install it correctly or something, and if you just do it from scratch, it usually works better. One thing I will also mention that is like a super annoying thing, that this is legacy stuff from the really past. Like I mentioned that it used to be that people were breaking their own computers for when they were installing Python like using the system Python and stuff like that. So back then, the people were using a lot of these pip install dash user. So they would install it for the user, like some package. But this is a really really like dangerous thing to do, because if you install some packages with this pip install user, those are now your packages. like those are the packages. Those will overwrite whatever environment you're using. So those will be always the first option that Python picks. And this is super annoying because like suddenly, like you create an environment, you start your Python, you try to do something, stuff breaks, and you don't know what is the problem. And later on, you realize that, okay, I had like a conflicting version of a package installed in my home directory with this pip install user, and it's usually hidden. Like those installed packages are usually hidden so that you don't immediately see those packages, and you have to go and look for them. And then you notice that, hey, like here's a package that was like Python took this package instead of the packages I wanted it to use. And like there was this kind of like there was this lion with a master key to all of the cages, and it was going and eating all of the gazelles. And it's like
So
I didn't
I
know
think,
that this could even happen, but this happened. So
yeah.
this is the kind of a like a situation you want to avoid. So do not, like, if you see instructions of pip install user somewhere, like I would highly recommend thinking about it and instead creating an environment and using pip install to install it into that environment.
Great advice. I think Enrico is getting ready now as well for the outreach outro. And also the home directory, that what you said, like especially if you want to distribute your code, you might not know exactly what to send because there's something always overriding. And also in a shared system, when you ask for support, you don't ship your home directory to your support staff, so it will be difficult to explain your problems. So how are you feeling, Enrico? Is everything good?
Yeah, this is super good.
Yeah.
I want to thank you so much, Sabri and Simo, for going again through something that is fundamental when it comes to reproducibility. In the last 3 minutes that we have for this course, I'm gonna cover a little bit of output or outro, sorry. So Simo, since you're sharing the screen, if you are able to
Yes.
browse to the list, to the program, kind of to the,
Yes.
you know,
You mean the main
maybe
page?
even there might be, or I can give you the link.
This one.
It's in the program page.
Let me
Yeah, this one here. So if you scroll to the end of day 3, there is this outro. And in practice, I'm not gonna keep it long, but just a reminder that you can get a credit for those of you who need credits. So the description of what to do is written in the web page, and if it's not clear, just get in touch, really. Maybe something that I want to mention is that I think all of the teachers that were involved in this course are actually involved with Code Refinery. Code Refinery is an organization that spans across multiple universities and other type of research organization in the Nordics. And the Code Refinery workshop runs twice a year, and we cover these type of topics like you basically saw today at the end. So reproducibility, opening your code, open licensing, and things like that. So definitely that would be the next step for those of you who want to, go deeper into some of the topics that you've seen today. But Code Refinery also covers version control. So the first week is all related to Git and GitHub and collaborating via Git and so on. So that was about future events. The next Code Refinery will be around March. We also run other open events. For example, at Alto, we will have this intro to HPC, and it's designed so that even if you are not at Alto, you can still learn something about Slurm and things like that. If you scroll a little bit more down, Simo, on the outro page, yeah, how to stay in touch. So we have both as Code Refinery and Alto Scientific Computing, we have mailing lists. So if you want to be added to those mailing lists, I guess that if you register to this course, there was a question if you want to be added. So if you click the yes, you will receive more advertisement for future courses, nothing else. It's a very low traffic mailing list. And you can also join us and work together with us. And the barrier again is extremely low, so that let's say that you find a typo or you have an idea to improve some examples, or you want to add a package that we didn't cover during the course, or our lessons are stored on GitHub. You can open an issue to a specific topic or start a conversation by getting in touch with us. And we are 1 minute over time. I can just mention that I will now paste in the notes document a Zoom link. So we will have the famous Zoom after party. I don't know if people are excited about Zoom after parties. But anyway, if you want to come to the Zoom after party, some of the instructors will be there and we can chit chat about the workshop. The Zoom after party will not be recorded or streamed or anything. So it's a safe space. All right, thank you again, Simo and Sabri and Jarno and Patricia and Nguyen and all the others that have been involved. I guess we can close the stream and let's keep in touch and have a beautiful November and December. See you. Bye bye.
See you.